Imagine having a time machine that allows us to travel back billions of years. What if we could witness the birth of stars, galaxies, and even the universe itself? While a literal time machine is beyond our reach, we have something almost as incredible, the James Webb Space Telescope, JWST. This state-of-the-art telescope is humanity's window to the past, peering an astonishing 13.5 billion years back in time, almost to the dawn of the universe itself. Let's explore how the JWST is transforming our understanding of the cosmos and revealing secrets from the universe's earliest moments. To truly appreciate the groundbreaking discoveries of the James Webb Space Telescope, JWST, we first need to understand the origins of the universe itself, the Big Bang. This wasn't an explosion in the way we usually think, like a bomb detonating. Instead, it was the sudden and incredibly rapid expansion of the universe from a single, unimaginably dense and scorching hot point. This event, which took place around 13.8 billion years ago, marked the birth of space, time, and all the matter that exists today. In the first few moments after the Big Bang, the universe was a turbulent, superheated ocean of energy and tiny particles moving chaotically with no structure. It was so hot, trillions of degrees, that atoms couldn't even form, let alone stars or planets. For hundreds of millions of years, the universe remained in this dense, glowing state, gradually expanding and cooling. Then, around 400 million years after the Big Bang, a monumental transformation began. The first atoms combined to create hydrogen and helium, the building blocks of stars. Gravity pulled these gases together, igniting the very first stars in the universe. As these stars formed, they clustered into the earliest galaxies, bringing light to what had once been a dark and featureless cosmos. This incredible period, known as the Cosmic Dawn, is exactly what the JWST is now peering into, capturing images and data from a time when the first galaxies were just beginning to shine, helping us uncover the secrets of our universe's distant past. The James Webb Space Telescope, JWST, is unlike any other telescope humanity has ever built. Launched on December 25, 2021, this engineering masterpiece orbits the Sun at a special location called the Second Lagrange Point, L2, about 1 million miles away from Earth. This position is not random. It allows JWST to remain in a stable orbit, away from Earth's heat and glare, providing an uninterrupted and crystal-clear view of the cosmos. What makes JWST truly groundbreaking is its ability to see in infrared light. Unlike visible light, which most telescopes rely on, infrared can pass through dust and gas, revealing objects hidden from view. More importantly, JWST's infrared vision is essential for studying the oldest galaxies and stars in the universe. This is because as the universe expands, light from distant celestial bodies stretches into longer wavelengths, shifting from visible light into the infrared spectrum, a process known as cosmological redshift. The farther away an object is, the more its light is stretched. Because JWST is designed to detect these faint, stretched-out infrared signals, it can peer deeper into space and further back in time than ever before. In essence, it acts like a time machine, allowing us to see the universe as it was over 13.5 billion years ago, just a few 100 million years after the Big Bang. This means JWST isn't just capturing breathtaking images, it's unlocking secrets about the birth of stars, the formation of galaxies, and the origins of our cosmic history. When the James Webb Space Telescope, JWST, sent back its first images, scientists were left in awe. The telescope had peered deep into the universe's past and captured something incredible, galaxies forming just a few 100 million years after the Big Bang. This was a time when the universe was still in its infancy, and yet what JWST revealed was a cosmic landscape teeming with activity. Astronomers expected to find only a few early galaxies, but instead they saw far more than anticipated. Not only were they numerous, but they also came in many unexpected shapes and sizes. This discovery suggests that the young universe was much more active and dynamic than scientists had previously believed. One of the most groundbreaking revelations was the detection of protogalaxies, the very first clusters of stars that would eventually merge to form the massive galaxies we see today. These protogalaxies were anything but orderly. Instead of smooth, well-defined structures like the spiral and elliptical galaxies we know, these early formations were chaotic, clumpy, and irregular. Stars were forming at astonishing speeds, with new ones igniting in rapid bursts. This challenges earlier theories that galaxy formation was a slow and steady process. Instead, JWST's findings suggest that the birth of galaxies was a turbulent and fast-paced event, reshaping our understanding of how the cosmos evolved in its earliest days. The James Webb Space Telescope isn't just spotting distant galaxies, it's uncovering some of the universe's very first stars, known as Population 3 stars. These ancient giants are unlike any stars we see today because they were born from the raw materials left behind by the Big Bang, primarily hydrogen and helium. Unlike modern stars, which contain heavier elements like carbon, oxygen, and iron, Population 3 stars formed in a universe that had never seen metals before. Scientists believe these stars were enormous, much bigger than our Sun, and burned incredibly hot and bright. Because they had no heavier elements to slow down their fusion process, they burned through their fuel at a furious rate, living short but dramatic lives. When they died, they exploded in titanic supernova blasts, some possibly even triggering rare pair instability supernovae, the most powerful stellar explosions known. These explosions scattered newly forged heavier elements into space, gradually enriching the universe with the building blocks needed for the formation of new generations of stars, planets, and even life itself. By discovering these long-extinct stars, scientists are piecing together the story of how the universe transformed from a simple, element-poor state into the rich, diverse cosmos we see today. Each new finding helps us understand the origins of the elements that make up everything, from the air we breathe to the very atoms in our bodies. One of the most groundbreaking discoveries made by the James Webb Space Telescope is its ability to shed light on two of the biggest mysteries in the universe: dark matter and dark energy. These invisible forces are not just minor cosmic players, they actually make up about 95% of the universe, yet scientists still don't fully understand them. Dark matter, which doesn't emit light or energy, can't be seen directly. However, JWST helps scientists detect its presence by observing how its immense gravity bends and distorts the light from distant galaxies. This effect, known as gravitational lensing, allows astronomers to map out where dark matter might be hiding and understand its role in shaping the universe's structure. Essentially, dark matter acts like a cosmic skeleton, influencing how galaxies form and evolve over billions of years. Then there's dark energy, the mysterious force causing the universe to expand at an accelerating rate. By using JWST to measure how fast galaxies are moving away from us, scientists can gather crucial data about dark energy's influence over time. This is a big deal because understanding dark energy could help answer one of the biggest cosmic questions. Will the universe expand forever, slow down, or collapse back in on itself? Looking back in time is fascinating, but the James Webb Space Telescope isn't just focused on the past. It's also searching for clues that could reveal life beyond Earth. One of its most important tasks is studying exoplanets, which are planets that orbit stars outside our solar system. Scientists believe that some of these distant worlds might have the right conditions for life, and JWST has the tools to investigate them. By carefully analyzing the gases in their atmospheres, JWST can look for specific chemical fingerprints that might hint at life. For example, if the telescope detects water vapor, it could mean the planet has clouds and maybe even rain. If it finds methane, scientists will wonder whether it comes from geological activity or biological processes like microbes. And if oxygen is present in large amounts, it could suggest the possibility of plant-like organisms producing it. Just imagine the moment when we finally confirm that life exists beyond Earth. It would change everything we know about the universe and our place in it. JWST is bringing us closer to solving one of the biggest mysteries of all time. Are we truly alone, or is life flourishing somewhere out there, perhaps in ways we've never imagined? The James Webb Space Telescope has made discoveries that both support and challenge what scientists thought they knew about the universe. Some of its findings have confirmed existing theories, but others have raised big questions that could change our understanding of how the cosmos works. One of the most surprising revelations is how quickly fully formed galaxies appeared after the Big Bang. According to our current models, Galaxies should have taken much longer to come together, slowly building up their structure over time. However, JWST has captured images of galaxies that seem to have assembled at an astonishing speed, far faster than scientists ever expected. This means the process of galaxy formation might work very differently than we previously thought, potentially forcing experts to rewrite major sections of astronomy textbooks. Another shocking discovery involves the massive black holes found at the centers of these ancient galaxies. Based on their age, these black holes should be relatively small, as they would not have had enough time to grow significantly. But JWST has detected some that are far larger than they should be, suggesting that black holes may form and expand much more quickly than our current theories allow. This raises deep questions about how black holes originate and evolve, challenging some of the fundamental ideas about the early universe. These unexpected findings prove that the universe still holds many secrets, and with JWST's advanced technology, scientists are just beginning to uncover them. Now let's take a moment to truly appreciate the groundbreaking technology that makes all of this possible. The James Webb Space Telescope boasts an enormous gold-coated mirror that spans more than 21 feet across. This mirror is specifically designed to capture the faint infrared light from faraway parts of the universe. The mirror isn't just one solid piece, it's made up of 18 hexagonal sections that unfolded in space, creating a stunning, intricate pattern that resembles a massive flower opening its petals. But the JWST's abilities go far beyond its mirror. It's equipped with state-of-the-art tools like high-powered cameras and spectrographs. These instruments are capable of analyzing light from stars and galaxies millions, even billions of light-years away. They break down the light into its individual colors, revealing crucial details about the star's makeup, how they're moving, and much more. With these advanced technologies, scientists are essentially performing cosmic archaeology, uncovering the universe's secrets by studying the faintest traces of light that have traveled across time and space. This is how they are able to piece together the grand, complex history of everything that exists. The James Webb Space Telescope stands as more than just an incredible engineering achievement. It represents the strength of global teamwork. While NASA took the lead in designing and building the telescope, two other space agencies, the European Space Agency, ESA, and the Canadian Space Agency, CSA, also played vital roles. ESA provided essential instruments, and CSA contributed both technology and funding to ensure the success of the mission. This massive international collaboration shows how science can bring nations together, encouraging countries from all over the world to join forces in their shared pursuit of knowledge. The JWST is a shining example of how, when we work together toward a common goal, we can accomplish remarkable things. It pushes the limits of what we know about the universe and marks a milestone in humanity's quest to explore the stars. As we look at the incredible discoveries made by the James Webb Space Telescope, it's hard not to feel excited about what lies ahead. The groundbreaking data it's collecting will be a treasure trove for researchers for many years to come, sparking curiosity and inspiring future generations of scientists and astronomers to push the boundaries of what we know. But the JWST is just one chapter in the ongoing adventure of exploring the universe. There are even more exciting missions on the horizon, like the Nancy Grace Roman Space Telescope, which will help us peer deeper into space, and the European Extremely Large Telescope, which promises to give us even sharper views of distant galaxies and stars. All of these powerful observatories will work together, unlocking more secrets of the universe as we strive to understand our origins and our place in the grand, infinite cosmos. These advancements are not just about science, they're about connecting with the very essence of who we are in the vastness of the universe. The James Webb Space Telescope has unlocked a whole new level of understanding about the vast universe. By peering back in time 13.5 billion years, it lets us witness the very beginning of the cosmos, providing us with insights we've never had before into how stars and galaxies formed. Every image and piece of data it sends back is like a treasure, giving us a rare look into where we come from, reminding us of how far we've come in our quest for knowledge, and sparking our curiosity for all the mysteries that are still out there. As we continue to explore the farthest reaches of space, one thing is clear: the JWST is more than just a telescope. It's a time machine that lets us travel to the past, a storyteller unraveling the history of the universe, and a bridge that brings us closer to the hidden wonders of the cosmos. The adventure has only just started, and the possibilities of what we might discover in the vast, unexplored depths of space are endless. The universe is incredibly expansive, and for centuries, scientists have been working to uncover its secrets. They've wondered where it all began, how it started, and how it's changed throughout history. One of the most intriguing parts of this exploration is a mysterious phenomenon called redshift. This phenomenon holds the key to understanding how the universe has been stretching out since its beginning. To truly understand redshift, it's helpful to first look at the basics of light and how it behaves. Light travels in waves, just like the ripples you see when you throw a stone into a pond. These waves come in different sizes or wavelengths, and each wavelength corresponds to a different color. For instance, light with a shorter wavelength appears blue, while light with a longer wavelength appears red. By studying the light from stars, galaxies, and other celestial objects, scientists can measure these wavelengths to uncover key details about the objects emitting the light. Now, redshift occurs when the wavelength of light gets stretched out, making the light shift toward the red end of the spectrum. Imagine the sound of a car speeding past you. As it moves away, the sound gets lower in pitch, a phenomenon called the Doppler effect. Light experiences something similar. Instead of sound, though, it's the light waves that stretch as the object moves away, making the light look redder. In space, when galaxies or other cosmic objects are moving away from us, their light gets stretched, creating redshift. The faster an object moves away, the more its light is stretched, and the stronger the redshift becomes. This shift is critical to understanding how the universe is expanding. By measuring the amount of redshift, scientists can determine how fast galaxies are moving and how far away they are. This discovery has been instrumental in shaping our view of the universe's structure and its vast, expanding nature. The idea of redshift is closely linked to the idea that the universe is constantly expanding. In the 1920s, the American astronomer Edwin Hubble made an important discovery that would change our understanding of the cosmos. While studying distant galaxies, Hubble noticed something remarkable. Galaxies were not staying still, but were actually moving away from Earth. Even more surprising was that the farther a galaxy was from Earth, the faster it seemed to be moving away. This observation led to Hubble's law, which states that the universe is expanding, with galaxies that are farther away moving faster. This finding provided one of the strongest pieces of evidence for the Big Bang theory, the idea that the universe began as an incredibly hot and dense point roughly 13.8 billion years ago and has been expanding ever since. The movement of galaxies away from us causes the light they emit to stretch, a phenomenon known as redshift. As the light waves are stretched, they shift toward the red end of the spectrum, hence the term redshift. When astronomers observe redshift in the light from distant galaxies, they can estimate just how far away those galaxies are. This is because the greater the redshift, the faster the galaxy is moving away, and therefore the farther it is. In a way, looking at the redshift is like peering into the past. The further the galaxy, the older the light we see. Essentially, the more red shifted the light is, the deeper in time we are looking, allowing us to observe events from billions of years ago and giving us a glimpse into the early stages of the universe's evolution. Now, let's dive into something really fascinating. How does redshift let us peer into the early stages of the universe? When we look at galaxies that are far, far away, we are actually seeing them as they were billions of years ago. The light that reaches us today has taken an extraordinary journey, sometimes traveling through space for over 13 billion years. This means when we observe these far-off galaxies with a strong redshift, we're not just seeing them as they are now, but rather as they were in the distant past. In other words, we're looking back in time to a point when the universe was much younger and still developing. The deeper we look into the past, the more we uncover about the beginnings of the universe. Galaxies with the highest redshift, which are the furthest from us, offer a rare window into a time when the universe was much smaller, hotter, and more packed with matter. These galaxies began forming only a few 100 million years after the Big Bang. By studying them, scientists can learn how the very first stars and galaxies took shape. It's almost like peeling back the layers of time, uncovering the universe's early years, and watching its story unfold before our eyes. This helps us understand the universe's evolution from a tiny, dense, and extremely hot state to the vast, expansive cosmos we see today. High redshift galaxies are like cosmic time capsules, offering a glimpse into the distant past of the universe. To study these galaxies, astronomers rely on advanced telescopes such as the Hubble Space Telescope and the James Webb Space Telescope. These powerful tools are equipped with specialized instruments that can capture incredibly faint light from galaxies located billions of light years away. When astronomers analyze the light from these high redshift galaxies, they can measure the level of redshift, how much the light has stretched as it travels across the vast expanse of space. The greater the redshift, the farther the galaxy is, and the older the light is. This stretching happens because the universe has been expanding since the light was emitted, so the farther we look, the earlier in time we see. This enables scientists to explore galaxies that formed just a few 100 million years after the Big Bang, when the universe was still in its infancy. It's a rare and extraordinary chance to observe the universe when it was much simpler, before the complex structures like stars, galaxies, and clusters took shape. How are the galaxies from the early universe different from the ones we observe today? In the distant past, galaxies were much smaller and less developed compared to the massive, well-formed galaxies we see around us now. During that time, these galaxies were still actively forming stars and collecting vast amounts of gas, which eventually fueled their growth into the large, mature galaxies we recognize today. When we observe galaxies at high redshifts, which represent an earlier time in the universe's history, we see that they were often small and irregular in shape. Unlike the smooth, organized structures of modern galaxies, these early galaxies lacked the clear, distinct features we now associate with mature galaxies. They were also undergoing dramatic processes, such as merging and colliding with other galaxies, events that played a crucial role in shaping their development and leading to the formation of the galaxies we are familiar with in the present day. These collisions often triggered bursts of star formation and were a driving force behind the evolution of these ancient systems. One of the most fascinating aspects of studying high redshift galaxies is that they offer a window into the birth of the very first stars, known as population 3 stars. These stars are believed to have emerged not long after the Big Bang, during a time when the universe was still largely filled with just hydrogen and helium gas. Over time, gravity pulled this gas together, causing it to collapse and eventually form the first stars and galaxies. The early stars that formed during this period were unlike anything we see in the universe today. They were far more massive, burning with incredible heat and at a much faster rate. Unlike modern stars, these ancient stars lacked heavier elements such as carbon, oxygen, and nitrogen, elements that play a crucial role in the formation of life. Instead, their makeup was almost entirely hydrogen and helium, the simplest elements in the universe. When these stars reached the end of their life cycles and explode as supernovae, they released enormous amounts of energy and created heavier elements like carbon, oxygen, and iron that would later form planets, other stars, and eventually life itself. These first stars and their explosive deaths were pivotal moments in the evolution of the universe, as they laid the foundation for the complex structures and life forms that would emerge billions of years later. Studying these distant galaxies gives scientists a clearer picture of how our universe transformed from a simple gas-filled expanse into the vibrant, star-filled sky we see today. By examining galaxies that are far away, scientists can gain valuable insights into the characteristics of the very first stars and how they impacted the development of the universe. These ancient stars were key players during a critical time called the reionization epoch. This was a moment in the universe's history when everything transitioned from being dark and foggy to clear and transparent. As the first stars began to shine, their light interacted with the surrounding gas, causing it to ionize. This process made it possible for light to travel freely across vast stretches of space, a crucial step in the universe becoming more transparent and allowing us to see farther into it. This transformation set the stage for the universe to evolve into the one we observe today. Redshift gives us a unique way to peer into the past, but it's not like the time travel we often see in science fiction. Rather than physically moving through time, we're observing the impact of time itself as light from faraway galaxies slowly makes its way to us. The farther out into space we look, the further back we can see in time. This is because light from distant galaxies takes millions or even billions of years to reach Earth. As it travels, it carries with it information about what the universe looked like long ago. By studying this light, astronomers can uncover details about the universe's early history, its formation, and how it has evolved over time. This method helps us understand everything from the birth of stars and galaxies to the development of cosmic structures, giving us a fascinating glimpse into the universe's past. When we study redshift and look at faraway galaxies, we are, in a way, traveling through time, not physically, but by observing light that has been traveling for billions of years. This light carries information from distant parts of the universe, showing us events that took place long before we even existed. It's like peeking into the past of the universe. These observations help us grasp how truly massive the universe is and how tiny our place in it is. The light we see from galaxies like Andromeda or even farther reaches of space has journeyed for millions, sometimes billions of years, giving us a snapshot of what the universe was like at that time. This makes the concept of time feel even more incredible. The study of redshift and distant galaxies is an exciting and rapidly growing area of research. Over the next few decades, these advancements could reveal much more about how the first galaxies, stars, and black holes were formed. We may even discover signs of life from distant worlds or uncover clues pointing to the existence of alien civilizations. As we continue to explore the redshift and the unfolding of cosmic history, we will expand our understanding of how the universe began and how it continues to evolve, possibly even opening doors to questions about time itself. Redshift is more than just a change in light color. It's a key to understanding the distant past. When we study galaxies with high redshift, we're essentially looking back in time, seeing the universe as it appeared when it was much younger. These galaxies act like time capsules, preserving secrets about the first stars, the birth of galaxies, and how the universe evolved over time. Through redshift, we get to experience a kind of time travel, watching the universe's earliest moments unfold as if they're happening now. This journey through time is both humbling and awe-inspiring. Each new discovery, each red-shifted galaxy, brings us one step closer to unlocking the universe's most ancient mysteries. Discoveries of early galaxies. Galaxies are immense clusters of stars, gas, dust, and dark matter, all bound together by the force of gravity. They can be found in a variety of shapes and sizes. Spiral galaxies, like our Milky Way, are shaped like a rotating disk with sweeping arms. Elliptical galaxies are more rounded, without distinct features, and tend to be older. And irregular galaxies lack any clear structure, often due to past collisions. These vast galaxies are not just scattered across space, they are the fundamental building blocks of the universe. Within their vast reaches, stars are born, live out their lives, and eventually die, often in explosive ways that shape the future of the galaxy. Galaxies are also the homes for planets, including Earth, as well as everything else that makes up our known universe, from asteroids to comets to dark matter. The size of galaxies can differ dramatically. Some are relatively small, holding only a few billion stars, while others are mind-bogglingly large, containing hundreds of billions or even trillions of stars. The Milky Way, our galaxy, falls somewhere in between, home to about 200 billion stars. In fact, there are billions of galaxies in the observable universe, each one with its own unique history, carrying clues to how the universe was formed and how it continues to evolve over time. Every galaxy, large or small, plays a crucial role in the ongoing cosmic story. Scientists have long thought that galaxies began to form just a few 100 million years after the Big Bang, the massive explosion that marked the start of everything we know in the universe. The Big Bang is believed to have occurred about 13.8 billion years ago, a time when the universe was still young and extremely hot. In these early stages, the only elements present were hydrogen and helium, which are the simplest and lightest elements in existence. As the universe cooled down, gravity played a key role. It pulled together vast clouds of gas and dust, causing them to collapse under their own weight. This process eventually led to the formation of the very first stars. Over time, these stars grouped together to create the first galaxies, which were very different from the galaxies we observe today. They were smaller, less complex, and mostly made up of just young, glowing stars with little to no heavy elements. These early galaxies laid the groundwork for the larger, more intricate structures that would evolve in the billions of years that followed. These early galaxies laid the groundwork for the larger, more intricate structures that would evolve in the billions of years that followed. The universe has been getting bigger ever since the Big Bang, with galaxies gradually drifting farther apart from each other. This expansion hasn't stopped, and what's even more surprising is that it's speeding up, something that has left scientists scratching their heads. As time passed, galaxies began to take shape and change. They collided with one another, merged together, and grew larger. These interactions helped create the massive and intricate clusters of stars, planets, and cosmic structures that we see today. But recently, the James Webb Space Telescope, JWST, has made some discoveries that have completely shaken up our previous understanding of how the universe works. One of the most shocking findings is the discovery of galaxies that formed far earlier than scientists ever thought possible. This unexpected revelation has turned many of our old ideas about the universe's early stages upside down. One of the most shocking discoveries made by the James Webb Space Telescope is the finding of galaxies that are much older than scientists ever imagined. According to our current understanding of the universe, the first galaxies were expected to start forming about 400 to 500 million years after the Big Bang. This idea was based on the assumption that it took time for the universe to cool down enough for stars to form from the leftover gas clouds of the Big Bang. But JWST has uncovered galaxies that seem to have appeared much sooner, only a few 100 million years after the Big Bang. What's even more surprising is that these galaxies look incredibly mature. They have well-organized structures and signs of stars actively being born, suggesting they formed much faster than scientists ever thought possible. This discovery is rewriting our understanding of how quickly the universe can evolve after such a monumental event. One of the most incredible discoveries made by the James Webb Space Telescope was the detection of a galaxy that formed only 230 million years after the Big Bang. This is truly surprising because it goes against what scientists believed about how quickly galaxies could emerge in the early universe. For a galaxy to form in such a short period, the conditions at that time must have been very different from what we previously imagined. It suggests that something about the early universe, whether the way matter gathered or how stars were born, must have worked in a way we didn't expect, opening up new possibilities about the history of our cosmos. These findings are incredibly significant because they shake up what we thought we knew about how galaxies and the entire universe came into being. There are several important details from these discoveries that don't quite fit with the current theories we have about cosmology. As we've seen, the incredibly fast formation of these early galaxies goes against the belief that galaxies formed slowly over long periods of time. If galaxies could appear so quickly, it makes us wonder about the conditions in the early universe. Was there something unusual about the environment back then that allowed galaxies to form at such a rapid pace? Could there have been hidden factors at work, like strange types of dark matter or unique mixtures of chemicals we didn't know about? These questions challenge the way we understand the universe's early stages and suggest there might be much more to the story than we thought. These ancient galaxies seem to be buzzing with activity, with many new stars being created inside them. In the early universe, scientists thought that star formation would be slow because there were not enough heavy elements like carbon and oxygen. These elements are crucial for making stars, as they are produced through nuclear reactions in the cores of older stars. However, if these ancient galaxies are forming stars at such a fast rate, it could mean that the conditions for star birth were much better than we originally thought. Alternatively, it might suggest that we were wrong about how the first stars came into existence in the first place. This discovery challenges our previous understanding and opens up new possibilities for how the universe evolved. Some of the galaxies that the James Webb Space Telescope has found are much bigger and more complex than scientists thought they would be, especially considering how old they are. These galaxies seem to have detailed, intricate shapes, and they host a wide variety of stars, which surprises researchers. This discovery goes against the old idea that galaxies in the early universe were small, simple, and lacked variety. These discoveries also spark curiosity about dark matter and dark energy, which are responsible for most of the universe's mass and energy, yet still remain largely unknown. Scientists have always been puzzled by them, but these new findings suggest that dark matter might have had a bigger impact on the creation of galaxies than we thought. It's also possible that dark energy influenced how fast the universe has been stretching out in ways that we still don't completely grasp. The more we learn, the more we realize just how much is still hidden from us, and how these mysterious forces might have shaped the universe in ways we never imagined. The recent surprising findings made by the James Webb Space Telescope could completely change the way scientists understand the universe's early days. It's becoming increasingly clear that the old theories about how the universe developed aren't entirely accurate. As a result, scientists will need to come up with new explanations to account for the rapid formation of ancient galaxies, something we didn't expect. This is an exciting moment in scientific research because it suggests that the next few years could bring discoveries that dramatically change our understanding of the universe's origins. As a result of these groundbreaking findings, scientists will need to rethink how galaxies form and evolve over time. This could mean re-examining old ideas about things like dark matter, star formation, and the overall structure of the universe when it was still young. The new evidence also hints that there is so much more to uncover about the first few 100 million years after the Big Bang, a period of time that remains full of unanswered questions and mysteries. These revelations open the door to deeper exploration of this era, and they could lead to a completely new chapter in our understanding of how the universe came to be. The discoveries made by the James Webb Space Telescope could provide answers to some of the biggest mysteries about the universe. For instance, scientists might uncover new details about how galaxies interacted with each other in the universe's early stages, possibly revealing that they were more connected than we once believed. Additionally, they may uncover more about the influence of supermassive black holes, massive objects thought to exist at the centers of most galaxies, and how these black holes might have played a key role in the development and growth of galaxies throughout history. These findings could completely change the way we view the cosmos and its evolution. The James Webb Space Telescope's discovery of the oldest known galaxies has completely changed the way we think about the universe. These galaxies, which formed much earlier and more rapidly than scientists predicted, shake up the current theories about how the cosmos began. This unexpected revelation opens up a whole new world of questions about the very beginnings of everything we know. While experts are still working hard to grasp the full meaning of these findings, one thing is certain: the universe is far more mysterious and incredible than we ever imagined. As the JWST continues to reveal the hidden wonders of space, we could be on the brink of uncovering a completely new story about how the universe was born and how it continues to grow. The future of studying the cosmos is incredibly exciting, and our quest to understand where we fit into the vast expanse of space is only just beginning. One of the most astonishing discoveries came from the study of a distant galaxy called GNZ 11, which lies an incredible 13.4 billion light-years away from Earth. This distance means we are observing the galaxy as it appeared just 400 million years after the Big Bang, making it one of the earliest galaxies ever detected. What is truly shocking is that GNZ 11 is far larger than scientists expected for a galaxy that is so young. With several 100 billion stars, it rivals galaxies like our Milky Way, which is much older and has had billions of years to develop and grow. But what makes GNZ 11 even more extraordinary is its incredibly fast growth rate. Not only is it much bigger than expected for its age, but it's also expanding much quicker than scientists ever thought was possible for a galaxy at this stage of the universe's history. This rapid expansion suggests that GNZ 11 had an abundant supply of gas, fuel for star formation, available at a time when the universe was still in its early stages. This finding has forced astronomers to rethink the models they've relied on to understand how galaxies form and evolve, since this galaxy's size and growth rate don't fit into the previous predictions. What's even more surprising is that scientists have discovered other massive galaxies from the early universe, and they're just as incredible. These galaxies, located millions or even billions of light-years away, are not only enormous but also appear to be very advanced. They contain many stars, have intricate structures, and some even have supermassive black holes at their centers. This is quite unusual because we thought that such large and complex galaxies wouldn't have formed until much later in the universe's history. The fact that they existed so early challenges everything we thought we knew about how galaxies grow and develop. The mystery that has scientists scratching their heads is how ancient galaxies could be so large and complex, especially when the universe was still in its infancy. At that time, the universe was still expanding and developing. So how did such massive and well-structured galaxies form so quickly? One possible explanation is a process known as direct collapse. Usually, galaxies form gradually as stars cluster together, pulling in surrounding gas and dust over millions of years. However, in the case of some ancient galaxies, a much faster method may have been at play. Instead of the slow buildup of stars and gas, these galaxies might have rapidly formed by collapsing directly from enormous clouds of gas. This collapse could have created massive galaxies in a fraction of the time it would take for typical galaxies to develop. This theory could explain how such large, well-organized galaxies existed so early in the universe's history. One other possibility is that the environment in the early universe was drastically different from what we see now. In the first few 100 million years after the Big Bang, the universe was filled with intense conditions. There were huge amounts of gas and radiation, creating a very chaotic and energetic atmosphere. This harsh environment could have played a major role in helping galaxies form quickly. The gas, pushed by the intense energy, may have been forced into dense areas that eventually became the stars and the structures of galaxies. With these extreme conditions, it's likely that galaxies grew much faster than scientists originally believed. The rapid formation might have been a result of the universe's powerful early forces. Some scientists believe that dark matter could have been crucial in the fast growth of large galaxies. Dark matter is a mysterious, invisible substance that doesn't give off light, but it still has mass, meaning it creates gravity. This gravity can influence how stars and galaxies move. It's possible that dark matter helped these early galaxies grow quickly by pulling in more gas and stars with its strong gravitational force. If dark matter was concentrated in certain areas of the early universe, it might have helped galaxies form faster and on a much larger scale than we expected. This would explain how some of the earliest galaxies grew so big, so quickly. One fascinating feature of these ancient galaxies is the discovery of supermassive black holes right at their centers. These black holes are truly enormous, containing millions or even billions of times the mass of our Sun. Typically, black holes form over a long period as massive stars collapse under their own gravity. But what makes these ancient galaxies so intriguing is that their supermassive black holes appear to have formed incredibly fast, much quicker than we would expect. This is especially puzzling because black holes of such enormous size should have taken billions of years to develop. Yet in some of these ancient galaxies, these giant black holes are already fully formed, prompting scientists to wonder how they were able to grow so rapidly in such a short time. The mystery deepens as researchers try to understand the forces and processes that could have caused this sudden and dramatic growth. One idea is that these massive black holes might have formed in a unique way called direct collapse. In this process, a huge cloud of gas, much bigger than anything we've seen today, could have collapsed straight into a black hole without first going through the usual stages of forming a star. Normally, stars form first, then evolve into black holes, but this direct collapse skips that step. This theory could help explain why these black holes are so enormous so soon after the universe began, much larger than we'd expect for their age. Another possibility is that these black holes grew rapidly by eating huge amounts of gas from the galaxies around them. As the black hole pulls in this gas, it can quickly grow in size, possibly even reaching enormous dimensions in a very short period of time. This would help account for their massive size in the early universe, a time when everything was still forming and evolving. The discovery of these enormous ancient galaxies has caused scientists to rethink many of the ideas they had about the early universe. For a long time, astronomers thought galaxies developed slowly, with stars gradually pulling together through the force of gravity. But these new discoveries show that some galaxies came together much faster than anyone had imagined. This has sparked fresh ideas about how galaxies actually form. Scientists are now exploring the possibility that galaxies might have formed through a mix of different processes, some of which were faster and more explosive than we originally believed. For instance, it could be that galaxies formed quickly in certain areas of the universe, while in other parts they took billions of years to develop. This new understanding opens up exciting possibilities for how the universe may have worked in its earliest stages, challenging previous beliefs and offering a deeper insight into the complex forces shaping the cosmos. These findings also lead us to ask some fascinating questions about how dark matter and black holes might have shaped the creation of galaxies. It's possible that dark matter played an even more significant part in forming galaxies than we ever thought before. At the same time, the enormous black holes at the centers of some galaxies might be connected to why these galaxies grew so quickly, hinting at a much deeper relationship between these mysterious forces and the universe's structure. The discovery of enormous ancient galaxies doesn't just change what we know about how galaxies come together. It could completely alter our view of the entire history of the universe. If galaxies were able to form so quickly and grow so large in the early universe, it might mean that the universe itself evolved much faster and in more complex ways than we ever imagined. This could point to the idea that the universe's early years were far more dynamic and lively than we thought. Instead of a slow, steady pace of development, the early universe might have been a time of rapid transformation, where galaxies grew at astonishing speeds and crashed into each other in spectacular, unpredictable ways. This could also shake up our understanding of the cosmic dark ages, a mysterious time right after the Big Bang when the universe was dark and empty before the first stars lit up the sky. What if that period wasn't as peaceful and uneventful as we assumed? It might have been a time of intense activity, with galaxies and stars forming at a much quicker pace than we ever expected. Most of the galaxies we observe today fall into two categories: spiral and elliptical. Spiral galaxies, like our Milky Way, are easily recognizable by their arms that gracefully curl outward, made up of stars, dust, and gas that orbit around a bright, centralized core. On the other hand, elliptical galaxies have a more rounded appearance, with stars moving in a variety of directions without a clear pattern. However, when astronomers look back in time, they find that early galaxies were very different. They were far more disordered. This difference in appearance comes down to how galaxies form. In the beginning of the universe, galaxies were much smaller and lacked the organized structure that we see in modern galaxies. Rather than having neat, sweeping arms or the smooth, elliptical shapes we're familiar with, these early galaxies were often irregular. Stars, gas, and dust were clumped together in random, uneven patches, making the galaxies look like they were still in the process of forming. It's as though they were caught in a constant state of chaos, constantly shifting, evolving, and yet following any discernible pattern or shape. This chaotic nature reflects the early universe's turbulent conditions, where galaxies were still colliding, merging, and developing into the more familiar forms we see today. Astronomers once thought that as galaxies aged, they would become well-structured and neatly organized. However, the earliest galaxies didn't fit this expectation. Instead of forming into smooth, regular shapes, they appeared as chaotic collections of stars and gas, still in the process of developing. Some galaxies were oddly shaped, with uneven lumps and clusters, while others seemed to be a mix of smaller galaxies still in the process of merging. This early stage of galaxy formation was a time of cosmic turmoil, where gravity was still pulling everything into place, and the galaxies were far from the smooth, organized structures we see in older, more mature galaxies today. How do we know what the earliest galaxies looked like, considering they are so far away and the universe is so ancient? The answer has to do with how light moves through space over time. Light doesn't travel instantly, it takes time to reach us. The farther an object is, the longer its light takes to arrive. In fact, when we observe galaxies that are billions of light years away, we're actually looking at them as they appeared billions of years ago. This is because the light we're seeing has been traveling through space for that long. In essence, observing distant galaxies is like peering into the past. For example, if we detect light from a galaxy 1 billion light-years away, we're witnessing it as it appeared 1 billion years ago, which means we're seeing it in the very early stages of the universe, when it was far younger and different from what it is today. Scientists rely on advanced telescopes, such as the Hubble Space Telescope and the James Webb Space Telescope, to capture stunning images of galaxies that are incredibly far away. These telescopes have the remarkable ability to observe galaxies billions of light-years from Earth, allowing us to peer into the past and see what the universe looked like in its infancy. By carefully examining these images, astronomers can uncover the shapes and structures of galaxies as they were when they first began to form. One of the most groundbreaking tools for exploring early galaxies is the James Webb Space Telescope. This telescope was specially built to study objects that are not only distant, but also extremely ancient. It can detect infrared light, which is key to studying galaxies whose light has traveled across vast distances, becoming stretched out into longer wavelengths. This unique ability helps scientists get a much clearer view of the universe's earliest galaxies. In fact, many of these galaxies appear more irregular and chaotic than astronomers had anticipated, challenging previous ideas about the orderly development of galaxies in the early universe. There are many ideas about why this chaotic appearance exists, and one of the most fascinating explanations involves dark matter. Dark matter is an invisible substance that makes up about 27% of the universe's total mass and energy. Unlike stars and planets, dark matter doesn't produce light or energy, which means we can't see it directly. However, scientists know it's there because of its powerful gravitational pull on objects we can see, like galaxies and clusters of stars. Without dark matter, galaxies wouldn't have enough gravity to hold themselves together. They would simply fly apart. Billions of years ago, when the universe was still young, dark matter wasn't spread out evenly. Instead, it formed dense clumps in certain regions of space. These clumps acted like giant cosmic anchors, pulling in vast amounts of gas and dust. Over time, these materials collapsed under gravity, leading to the birth of new stars and eventually entire galaxies. However, because dark matter was scattered unevenly, the galaxies that formed around it weren't neatly structured like the spiral galaxies we see today. Instead, they were twisted, irregular, and chaotic, still being shaped by the gravitational forces of dark matter. This explains why some of the earliest galaxies looked so disorganized. Over time, they would evolve into the more structured forms we recognize in the modern universe. In the early days of the universe, galaxies were much smaller and packed closely together. Instead of the vast, isolated spirals and ellipticals we see today, the cosmos was filled with tiny galaxies drifting near one another. Because they were so close, many of them eventually crashed into each other and combined, leading to the strange, irregular shapes we observe in ancient galaxies. But despite these massive cosmic collisions, the individual stars inside the galaxies almost never smashed into one another. That's because stars are separated by immense distances. However, the gas and dust floating between them were a different story. When galaxies merged, their swirling clouds of gas and dust collided, compressing and heating up in the process. This often sparked the birth of brand new stars, altered the paths of existing ones, and reshaped the galaxies entirely. Over time, these smaller galaxies kept merging, forming larger and larger structures. This chaotic process played a big role in shaping the universe as we know it. Even today, galaxies still collide, but back in the early universe, when everything was more densely packed, these cosmic smash-ups happened much more often, making galaxy mergers a key part of their evolution. In the early universe, galaxies contained much more gas than the galaxies we see today. This gas, primarily hydrogen and helium, served as the raw material for forming new stars. Because there was so much of it, early galaxies were chaotic and often had irregular shapes rather than the well-structured spirals or ellipses we see now. Instead of settling smoothly into organized formations, the gas could be unevenly distributed, creating a scattered and disorderly appearance. The way stars formed back then was also quite different from how they form today. In modern galaxies, star formation tends to be more controlled and happens in concentrated regions, such as the spiral arms of galaxies like the Milky Way. But in the early universe, the process was much more chaotic and rapid. Stars could form almost anywhere within a galaxy, often in bursts triggered by turbulent conditions or galaxy mergers. This random and unregulated pattern of starbirth contributed to the irregular and sometimes clumpy appearance of early galaxies. This difference in structure and star formation is partly due to the fact that galaxies in the early universe were still evolving. Over time, as galaxies merged and matured, they developed more defined shapes and organized systems of star formation. However, by studying these ancient, disorderly galaxies, astronomers can gain valuable insights into how the universe evolved and how the massive, structured galaxies of today came to exist. At the heart of most large galaxies, including our Milky Way, lies a supermassive black hole, an incredibly dense and powerful object with gravity so intense that nothing, not even light, can escape once it gets too close. These black holes are not just passive objects, they actively shape their galaxies in profound ways. Scientists believe that even in the early universe, when galaxies were still forming, supermassive black holes had already started to take shape at their centers. Their immense gravitational pull could have drawn in vast amounts of gas, dust, and even entire stars, influencing how these young galaxies evolved. In some cases, this pull might have caused galaxies to become turbulent and disordered, with stars moving in unpredictable ways rather than settling into neat structures. But black holes don't just pull things in, they can also release astonishing amounts of energy. When matter spirals toward a black hole, it heats up to extreme temperatures, creating powerful bursts of radiation. Some black holes even produce jets of high-energy particles that shoot out at nearly the speed of light, blasting through space and potentially reshaping the galaxy around them. These outbursts could have disrupted star formation, altered the distribution of gas and dust, and contributed to the chaotic, irregular shapes seen in some of the earliest galaxies. Even today, scientists are still working to fully understand how supermassive black holes influenced the universe's early years. But one thing is clear. These cosmic giants were not just passive spectators. They played a major role in shaping the galaxies we see today. As the universe grew older, galaxies started to take on more recognizable shapes. In the early days, shortly after the Big Bang, the universe was a chaotic place filled with swirling clouds of gas, dust, and newly forming stars. These early galaxies had irregular and unpredictable shapes, often looking more like scattered clumps than the majestic spirals and smooth ellipses we see today. Over billions of years, a powerful force shaped these galaxies: gravity. The invisible pull of gravity caused galaxies to interact, sometimes colliding and merging in dramatic cosmic events. When two galaxies merged, their stars didn't crash into each other directly because of the vast distances between them, but their combined gravitational forces stirred up gas and dust, triggering new waves of star formation. Over time, the once chaotic galaxies settled into more organized structures, forming the elegant spiral arms of galaxies like the Milky Way or the smooth, rounded shapes of elliptical galaxies. Even today, the universe is not done evolving. Galaxies continue to grow and change, merging with one another and reshaping their structures. In fact, our own Milky Way is on a collision course with the nearby Andromeda galaxy, a process that will unfold over the next few billion years. Eventually, the two galaxies will combine into a single larger galaxy, proving that the grand dance of galaxy formation and transformation is still far from over. The recent discovery that early galaxies were far more chaotic than scientists had previously imagined is a game-changer for our understanding of the universe. This finding challenges old ideas about how galaxies form, suggesting that the process is far more complicated than we thought. The unusual irregular shapes of these early galaxies reveal that the universe during its infancy was much more unpredictable. The exact forces and conditions that influenced the formation of these galaxies are still not entirely clear, and this mystery continues to puzzle researchers. These early galaxies can be seen as the universe's first building blocks, offering valuable clues about how galaxies come into being, grow, and change over time. By closely examining these strange, disordered galaxies, scientists are piecing together the history of the universe. This research helps us better understand how the universe evolved from a wild, chaotic state into the organized, structured cosmos that we observe today. The study of these early galaxies is not only shedding light on the past, but also revealing the complex forces that shaped everything we see around us now. The strange and unusual shapes of the first galaxies are one of the most intriguing parts of the universe's past. These wild, unpredictable forms offer valuable clues about how galaxies are born, collide, and change over time. As technology gets better and we learn more about the far-off parts of space, we may unlock even more mysteries about the early universe. Right now, studying these ancient galaxies is just getting started, and with every new finding, we get a little closer to grasping the true nature of the universe and the powerful forces that have shaped it. One of the most thrilling discoveries in modern astronomy is the detection of what scientists call the earliest light. This light comes from galaxies that formed just 200 to 300 million years after the Big Bang, providing us with an incredible glimpse into the universe's earliest days. Light particles, called photons, were trapped because the universe was filled with a thick fog of particles. One of the most thrilling discoveries in modern astronomy is the detection of what scientists call the earliest light. This light comes from galaxies that formed just 200 to 300 million years after the Big Bang, providing us with an incredible glimpse into the universe's earliest days. Light particles, called photons, were trapped because the universe was filled with a thick fog of particles. These particles interact with photons, scattering them in all directions and preventing light from traveling freely. It took hundreds of thousands of years for the universe to cool down and expand enough to allow light to move freely. This moment, when light could finally escape, marks the beginning of what we refer to as the cosmic microwave background, CMB, the faint glow we detect from the early universe. The light we see today from the first galaxies, which appeared 200 to 300 million years after the Big Bang, is truly extraordinary. It's one of the earliest sources of starlight ever to be emitted in the entire universe. This light is a result of the birth of the very first galaxies and stars, signaling a major turning point in the universe's history. Before this, the universe was like a thick, cloudy fog made of particles, blocking any light. But as the first stars and galaxies formed, they began to clear the fog, allowing light to shine through and fill the vast space. This moment marked the universe's transition from darkness to a brilliant, sparkling expanse full of stars and galaxies, laying the foundation for the cosmic landscape we observe today. The significance of this discovery lies in the fact that scientists have essentially uncovered the earliest light from the universe, light that has traveled for billions of years to reach us. It holds the secrets to understanding the cosmic dawn, a pivotal time when the very first stars and galaxies started to form out of the chaotic, dense cloud of gas and energy that existed right after the Big Bang. This discovery of light from galaxies that formed just 200 to 300 million years after the Big Bang is a groundbreaking achievement. It offers an unprecedented window into a time long before our own solar system or even our galaxy came into existence. This era, known as the Cosmic Dawn, is key to unraveling how the universe evolved. From the extremely hot and dense conditions immediately following the Big Bang, it slowly expanded and cooled, eventually giving rise to the diverse and intricate universe we observe today. Scientists had suspected for years that galaxies started forming during this period, but proving this theory was a huge challenge. The main reason for this difficulty is the immense distances between us and these early galaxies. In space, the farther away an object is, the longer its light takes to reach Earth. For galaxies formed billions of years ago, their light has traveled across vast stretches of space, making it extremely faint by the time it arrives here. Moreover, the light has shifted to longer wavelengths, moving beyond the range of what our eyes can see. This shift, particularly into infrared wavelengths, makes it necessary to use specialized technology like powerful telescopes to detect and study this faint, stretched light. Without these advanced tools, observing such distant galaxies would be nearly impossible. To detect the very first light in the universe, scientists needed super-sensitive instruments, advanced telescopes, and a deep knowledge of how light travels through space. This incredible discovery was made possible by cutting-edge technology, including the James Webb Space Telescope from NASA, the Hubble Space Telescope, and powerful telescopes on Earth capable of detecting infrared light, which is invisible to the human eye. These telescopes could pick up faint signals from the distant past, helping scientists peer back to the early stages of the universe, just moments after the Big Bang. The collaboration between space-based and ground-based observatories was key to uncovering this ancient light, shedding light on the cosmos's beginnings in a way never seen before. One of the biggest hurdles in finding this ancient light is the fact that the universe has been stretching out ever since the Big Bang. As it expands, the light traveling through space gets stretched too, causing its wavelength to grow longer. The light that originally came from the very first galaxies, which was once in the ultraviolet and visible spectrum, ends up being stretched so much that it now falls into the infrared range by the time it reaches us. This is why telescopes that can capture infrared light are absolutely crucial for spotting these distant early galaxies. The James Webb Space Telescope is designed specifically to see in the infrared spectrum, allowing it to peer far into the depths of space and detect light that our eyes would never be able to see. It opens up a whole new way to look at the universe and discover parts of it that have been hidden for billions of years. The light we can see from galaxies that appeared just 200 to 300 million years after the Big Bang reveals a lot about the very beginning of the universe. It shows that the first galaxies and stars came together much sooner than we might have expected after the Big Bang. This discovery helps answer one of the most important questions scientists have. How quickly did the universe start to form organized structures like galaxies after its explosive start? This discovery gives us an exciting glimpse into the very first stars that ever existed, known as Population 3 stars. These ancient stars were vastly different from the ones we see in the night sky today. They were primarily made of hydrogen and helium, the two simplest and most abundant elements that came into existence during the Big Bang. What made them truly unique was that they didn't contain any metals, which are elements heavier than hydrogen and helium. Because of this, these stars burned much hotter and much faster than the stars we are familiar with now. Their intense energy and short lifespan meant they lived fast and died young. These early stars played a crucial role in shaping the universe, helping to ionize the vast stretches of gas that filled space. This process turned the gas from being neutral into ionized particles, allowing light to travel freely across the universe for the first time, unlocking the potential for the cosmos to become what we see today. The light that has been detected gives us valuable hints about how galaxies were formed. In the beginning, galaxies were probably much smaller and more uneven than the ones we observe today. Over time, these tiny, irregular galaxies collided and merged with one another, gradually becoming the massive galaxies we are familiar with now. By examining the characteristics of these early galaxies, scientists can uncover more details about how galaxies develop and expand over billions of years, helping us understand the long journey of their growth and transformation. The first light that reached us from the early universe has a special connection to one of the most puzzling and elusive things in space: dark matter and dark energy. Even though these two forces make up most of the universe's mass and energy, we can't actually see them. Dark matter is believed to play a key role in the creation and movement of galaxies, while dark energy is thought to be behind the universe expanding faster and faster over time. This ancient light offers scientists a unique opportunity to understand more about how dark matter influenced the universe in its earliest days. Unlike ordinary matter, dark matter doesn't interact with light, so it doesn't glow or shine. However, it does have a strong gravitational pull that affects how galaxies form and move. By studying how galaxies came together in the beginning of the universe, scientists can uncover more secrets about these invisible forces that helped shape everything. As we keep studying the universe, we will keep finding more of this ancient light. Every new discovery brings us closer to understanding how the universe started, how galaxies came together, and how it has changed into the vast cosmos we see now. The more we uncover this ancient light, the clearer our understanding becomes of the powerful forces that shaped everything around us, and our place in it. This study of ancient light also opens exciting doors to understanding time and space in new ways. The light we're observing now started its journey millions of years ago, which means we're actually looking back in time. We're able to witness events that happened long before Earth or even our solar system existed. It's like peering into a time when the universe was completely different, watching the incredible transformations that led to the world today. The discovery of light from galaxies that formed only 200 to 300 million years after the Big Bang is just the beginning of an exciting journey into the past of our universe. It's only the first step in what promises to be a groundbreaking exploration. With the rapid development of more powerful telescopes and cutting-edge techniques, scientists are poised to dig even deeper into the mysteries of the cosmos. The early universe remains full of unknowns, and every new piece of data we uncover brings us one step closer to answering the most profound questions about how everything in existence, our planet, the stars above us, and the entire universe, came to be. Looking ahead, researchers are eager to discover even more about the earliest galaxies, the very first stars, and the dramatic processes that shaped the universe into the complex structure we see today. The study of light emitted from these ancient galaxies will continue to be a crucial method for unlocking the hidden secrets of the universe, allowing us to trace the origins of everything we know, from the brilliant stars that light up the night sky to our own place in this vast and ever-expanding cosmos. As we explore further, we may even begin to understand the forces that sparked the birth of the universe and the very fabric of time itself. The discovery of light from galaxies that were born just 200 to 300 million years after the Big Bang is one of the most thrilling and groundbreaking moments in modern astronomy. This incredible find allows us to peer back in time, offering a glimpse of the very first stars and galaxies that began to form after the universe's birth. The light we see today is like a time capsule, providing us with vital clues about how galaxies came into existence, the elusive forces of dark matter and dark energy, and the overall evolution of the cosmos. Thanks to the rapid progress in technology, especially with powerful tools like the James Webb Space Telescope, we now have the ability to look deeper into space than ever before. This advanced technology is enabling us to explore distant parts of the universe, revealing secrets that were once beyond our reach. By studying this ancient light, we are unlocking the mysteries of how everything we see in the universe came to be. As we continue to explore, we will uncover even more astonishing truths, helping us understand our own origins and our place in the vast, unknown expanse of the universe. The more we learn, the more we realize how interconnected everything is and how much more there is to discover about the universe's early days and the forces that shaped it. Imagine the universe right after the Big Bang, a chaotic, high-energy place filled with swirling matter and intense radiation. Everything was expanding rapidly, and tiny differences in density appeared throughout space. Some areas had more mass packed into them than others, and this imbalance led to something extraordinary: the possible birth of primordial black holes. Unlike the black holes we usually think of, those that form when giant stars run out of fuel and collapse, primordial black holes may have emerged directly from the fabric of space itself. They didn't come from dying stars. Instead, they were born from the extreme conditions present in the very first moments of the universe. Right after the Big Bang, space wasn't uniform. Some regions were denser than others, and gravity pulled these dense spots together. If a particular region became dense enough, it could collapse under its own gravity and form a black hole, even without a star involved. These primordial black holes could have appeared just fractions of a second after time itself began, making them some of the oldest objects in existence, if they still exist today. Scientists believe that these ancient black holes, if they formed in significant numbers, could help explain dark matter, the mysterious invisible substance that makes up most of the universe's mass. Some might have evaporated over time due to a process called Hawking radiation, while others, if large enough, could still be drifting through space today, hidden from view, but influencing their surroundings with their immense gravitational pull. Scientists believe that primordial black holes may have formed in the very first moments after the Big Bang, during a time when the universe was an unimaginably hot and dense place. In these early fractions of a second, tiny but extremely compact regions of space could have collapsed under their own immense gravitational pull, creating miniature black holes. Unlike the supermassive black holes we see at the centers of galaxies today, these primordial black holes would have been incredibly small, possibly no larger than a proton. However, despite their tiny size, they could still pack a serious punch, holding a huge amount of mass in a minuscule space. Some scientists estimate that such black holes could have had masses ranging from that of an asteroid to even a fraction of Earth's mass. These ancient black holes, if they exist, might still be lurking in the universe today, hidden in the vastness of space. Some theories even suggest they could be a major part of dark matter, the mysterious substance that makes up most of the universe's mass, but remains invisible to our telescopes. If we can prove they exist, it could unlock deep secrets about the early universe and the fundamental nature of gravity. In the first moments after the Big Bang, the universe was an incredibly hot and dense place, filled with a chaotic mix of energy, radiation, and tiny particles. Unlike today's vast and structured cosmos, everything was packed together in an almost unimaginable state of high pressure and heat. During this early period, the distribution of matter was not perfectly even. Some regions were slightly denser than others due to random fluctuations. In most cases, these tiny differences in density evened out over time as the universe expanded. However, in some rare instances, certain areas were so dense that instead of spreading out, they collapsed inward under their own gravitational pull. This collapse led to the formation of what scientists call primordial black holes, small but incredibly powerful objects that could have existed since the dawn of time. Unlike the black holes we know today, which typically form when massive stars run out of fuel and collapse, these primordial black holes were born from the extreme conditions of the early universe itself. Some of them could have been as tiny as an atom, yet packed with immense energy, while others might have grown larger over time. If they still exist, they could hold crucial clues about the early universe and even help explain mysterious cosmic phenomena, such as dark matter. These black holes are called primordial because scientists believe they were formed during the earliest moments of the universe, long before stars, planets, or galaxies even existed. Unlike the black holes that form today when massive stars collapse, these ancient ones may have emerged within the first few seconds or minutes after the Big Bang. During this brief but extreme period, the universe was an incredibly hot and dense sea of energy and particles. If certain regions had just the right conditions, such as areas of intense pressure and density, gravity could have caused them to collapse into tiny but incredibly massive black holes. These primordial black holes might still exist today, hidden across the universe, and some theories suggest they could even make up a portion of dark matter, the mysterious substance that scientists believe accounts for most of the universe's mass. Primordial black holes are a very different kind of black hole compared to the ones we usually hear about. Most black holes form when massive stars reach the end of their lives and collapse under their own gravity. These are called stellar black holes, and they can be anywhere from a few times the mass of our Sun to dozens of times heavier. However, primordial black holes are believed to have formed in a completely different way, right after the Big Bang during the early moments of the universe. Because of this, they don't necessarily have to be large. In fact, scientists think some primordial black holes could be incredibly tiny, possibly as small as a single atom. Despite their tiny size, they would still be incredibly dense, packing an immense amount of mass into such a minuscule space. This makes them fascinating to scientists, as they might behave very differently from the black holes we commonly study. Some researchers even believe these tiny but powerful objects could help explain certain mysteries of the universe, such as dark matter. Unlike stellar black holes, which are created when massive stars run out of fuel and collapse under their own gravity, primordial black holes are thought to have formed in a completely different way, long before stars even existed. Scientists believe that in the chaotic early universe, just moments after the Big Bang, tiny but powerful fluctuations in the density of matter could have caused some regions to collapse into black holes. This means primordial black holes didn't come from dying stars. They may have appeared spontaneously in the extremely dense and energetic conditions of the young cosmos. Because they formed so early, primordial black holes might be far more common than we realize. Some scientists speculate that they could be scattered across the universe, hidden in the vastness of space, possibly even lurking within our own galaxy. Their small size and dark nature would make them nearly impossible to detect directly, but their gravitational influence could still leave clues. In fact, some researchers suggest that primordial black holes could help explain some of the biggest mysteries in astrophysics, like dark matter, the invisible substance that makes up about 85% of the universe's total mass. If true, these ancient black holes could be the missing puzzle piece that unlocks one of the greatest cosmic enigmas. At first, primordial black holes might appear to be just a fascinating idea, something that only exists in theory. After all, there's no direct proof they're real, not yet anyway. However, scientists are investigating a number of ways to find evidence for these mysterious objects, and some clues hint that they could indeed exist. One of the most exciting pieces of evidence comes from something called gravitational waves. These waves are like ripples in the fabric of space-time, created when massive objects, like black holes, collide. In recent years, scientists have detected these gravitational waves, and some of them might have been caused by the merging of primordial black holes, objects that formed right after the Big Bang. If scientists keep detecting more gravitational waves from sources they weren't expecting, it could provide strong proof that primordial black holes are real and hiding in the vastness of space. One way scientists search for clues about the universe's past is by studying cosmic microwave background, CMB, radiation. This faint glow is the leftover heat from the Big Bang, still lingering in space after nearly 14 billion years. By analyzing this radiation, researchers can uncover secrets about the early universe. If tiny black holes, called primordial black holes, formed in the first moments after the Big Bang, they might have disturbed this ancient radiation. These disturbances could leave behind subtle patterns or fingerprints that advanced telescopes and instruments might be able to detect. But that's not all. Primordial black holes could also help solve one of the biggest mysteries in astronomy: dark matter. Scientists know dark matter exists because they see its effects, like how it bends light from distant galaxies and influences the movement of stars, but they've never been able to see or touch it. That's because dark matter doesn't emit or reflect light, making it completely invisible. However, it does have gravity, which means it can pull on things we can see. If primordial black holes are out there, they could be acting as dark matter, explaining the mysterious force that holds galaxies together and shapes the structure of the universe. Primordial black holes are incredibly fascinating because they might hold the key to understanding the birth of the universe itself. Unlike the black holes we know today, formed from the collapse of massive stars, these mysterious objects would have come into existence long before stars, galaxies, or even light had a chance to appear. Imagine a time when the universe was still a chaotic sea of energy and particles, barely moments after the Big Bang. If primordial black holes were formed in this era, they would be like ancient relics, frozen in time, carrying secrets from the universe's earliest days. Studying these ancient black holes could give scientists a rare opportunity to peek into the conditions of the universe when it was still in its infancy. They could provide clues about the immense forces that shaped everything we see today, from planets to galaxies and even the fundamental laws of physics. But their significance doesn't stop there. Some scientists believe that primordial black holes might actually be the missing puzzle piece in one of the biggest mysteries in physics, the true nature of dark matter. Dark matter makes up most of the mass in the universe, yet it remains invisible and undetectable except through its gravitational pull. If primordial black holes turn out to be responsible for dark matter, it would completely change our understanding of the cosmos, opening the door to entirely new discoveries in astrophysics and cosmology. If primordial black holes really exist, they could shake up everything we think we know about physics. These mysterious objects might hold secrets about gravity, quantum mechanics, and the very fabric of space and time. Scientists believe that by studying them, we could uncover hidden laws of the universe, ones that might finally connect Einstein's theory of general relativity, which explains how massive objects bend space and time, with quantum physics, which governs the tiniest particles in existence. If we could bridge this gap, we might move closer to solving one of the biggest mysteries in science: the search for a single, all-encompassing theory of everything that explains how the universe truly works. Primordial black holes remain one of the greatest mysteries of the universe, and scientists are only beginning to scratch the surface of what these strange objects might reveal. We haven't yet found direct proof that they exist, but the clues we've gathered so far suggest they could be a missing piece in the puzzle of how the universe began. These ancient black holes are thought to have formed in the first moments after the Big Bang, possibly holding secrets about the birth of galaxies, the mysterious substance known as dark matter, and the invisible forces that control the cosmos. As telescopes, satellites, and scientific methods improve, researchers are hopeful that they will uncover more evidence, bringing us closer to understanding whether primordial black holes really exist and what role they played in shaping the universe as we know it. The universe is unimaginably huge, and despite all our discoveries, there is still so much we don't understand. Among its many mysteries are primordial black holes, ancient, invisible objects that may have formed in the earliest moments after the Big Bang. These cosmic enigmas are not just fascinating. They could hold the key to unlocking the secrets of how the universe itself came into existence. Scientists are eager to study them because understanding these mysterious black holes might help us piece together the story of the universe's birth, making them one of the most thrilling frontiers in modern science. When we look into the vastness of space using incredibly powerful telescopes, we aren't just observing distant galaxies, we're actually traveling back in time. This might sound like science fiction, but it's a fascinating reality of how light works. Light doesn't travel instantly. It moves at a fixed speed, about 186,000 miles per second. While that's incredibly fast, space is so vast that light from the most distant galaxies takes millions or even billions of years to reach us. That means when we observe these faraway galaxies, we're not seeing them as they are today, but as they were long ago, sometimes from a time when the universe was still young. As scientists study these ancient galaxies, they have made a discovery that shakes the very foundations of our understanding of the cosmos. Within some of these galaxies, they've found supermassive black holes, gigantic objects with gravitational pulls so strong that not even light can escape. The shocking part is, these black holes seem to have formed far earlier than our current scientific models say is possible. Black holes are already among the most mysterious and puzzling objects in the universe. According to the best theories we have, black holes start small, usually from the collapse of a massive star, and then grow larger over millions or even billions of years by pulling in gas, dust, and even entire stars. But the black holes found in these ancient galaxies appear to have already reached their enormous sizes when the universe was still in its infancy. That means they must have formed much faster than our current understanding of physics allows. Based on what we know, black holes should take vast amounts of time to reach such immense sizes. They need to consume enormous amounts of matter, and the process is thought to be gradual. But these newly discovered black holes skipped the waiting period. They were already gigantic at a time when the universe itself was just starting to take shape. Some scientists believe there might have been a special process in the early universe that allowed black holes to grow much more quickly than they do today. Others speculate that perhaps the first black holes were created in a completely different way, possibly from enormous clouds of collapsing gas rather than from dead stars. Before we dive into the depths of this cosmic enigma, let's first break down what a supermassive black hole actually is. To put it simply, a black hole is a place in space where gravity is so unbelievably strong that nothing, not even light, the fastest thing in the universe, can escape its pull. Once something crosses a black hole's invisible boundary, known as the event horizon, it is gone forever, swallowed up by the darkness. Black holes come in different sizes, from relatively small ones formed when massive stars explode to truly gigantic ones known as supermassive black holes, SMBHs. These cosmic giants are on an entirely different level. They are not just a few times bigger than our Sun. They can be millions or even billions of times more massive. Imagine compressing an entire galaxy's worth of material into a single point. That's the sheer power of an SMBH. These massive objects are not just floating randomly in space. Instead, they are found at the very hearts of galaxies, including our own Milky Way. It's almost as if they are the rulers of the galaxies, silently pulling the strings behind the scenes. Scientists believe that SMBHs play a vital role in shaping the universe as we know it. One of their most important functions is influencing the formation and evolution of galaxies. Their immense gravitational pull affects how stars move, where gas clouds gather, and even how new stars are born. In some cases, they can trigger violent outbursts, shooting powerful jets of energy across vast distances, altering the structure of entire galaxies. In the Milky Way, astronomers have identified a supermassive black hole called Sagittarius A*, which sits at the very center of our galaxy. Even though it is invisible to the naked eye, scientists can observe its effects by studying the movement of stars around it, whirling at mind-boggling speeds as if they are caught in an unseen whirlpool. Despite their name, black holes are not just voids of nothingness. They are dynamic and powerful cosmic forces that have been shaping the universe for billions of years. Some scientists even believe that without SMBHs, galaxies might not exist in the way we see them today. Supermassive black holes are some of the most mysterious objects in the universe. They don't just appear out of nowhere. Instead, they take an incredibly long time to form. According to everything we know about physics, their growth should be a slow and gradual process. To understand this, let's start from the beginning. Black holes typically start out as much smaller objects known as stellar mass black holes. These are formed when enormous stars reach the end of their life cycles and explode in violent events called supernovae. After this explosion, the remaining core of the star collapses under its own gravity, creating a black hole. Once a stellar mass black hole forms, it doesn't stay small forever. It begins to consume everything around it, gas, dust, and even entire stars, pulling in matter with its immense gravitational force. Over time, as it devours more and more material, it grows larger. Scientists believe this process can take billions of years before a black hole reaches the supermassive stage, where it can be millions or even billions of times heavier than our Sun. But here's where the real mystery begins. When astronomers peer deep into space, essentially looking back in time, they have discovered something shocking. Fully formed supermassive black holes existed less than 1 billion years after the Big Bang. This is a huge problem because, according to our current understanding of physics, there simply shouldn't have been enough time for them to grow so massive. If black holes need billions of years to reach such gigantic sizes, how could these early ones have already become so enormous? It's like finding a fully grown tree in a place where you know the seed was only planted a few days ago. This discovery has left scientists puzzled and has led to some serious questions about whether we truly understand how black holes grow. According to what we know from standard physics, black holes should have formed much later in the universe's history. The process begins with massive stars, the kind that burn brightly for millions of years before running out of fuel. When these gigantic stars die, their cores collapse under their own immense gravity, forming black holes. These newly formed black holes are relatively small at first, but over billions of years, they can grow by merging with other black holes and by pulling in gas and dust from their surroundings. Eventually, after countless cosmic collisions and the steady accumulation of matter, some of them become the supermassive black holes that sit at the centers of galaxies today. But here's where things get incredibly strange. Astronomers have discovered supermassive black holes in galaxies that existed just 700 million years after the Big Bang, an incredibly short time on the cosmic scale. To put it in perspective, the universe is 13.8 billion years old, meaning these monstrous black holes were already fully grown when the universe was still in its infancy. This discovery is mind-blowing because, according to everything we understand, there simply wasn't enough time for black holes to reach such enormous sizes so quickly. By our current knowledge, the growth of black holes should be a slow and gradual process. But these ancient black holes seem to have skipped the usual stages of development and appeared fully formed, as if they had been there from the very beginning. So how did this happen? Scientists are now faced with one of the biggest cosmic mysteries of our time. Some researchers propose that these black holes may have formed from massive clouds of gas collapsing directly into black holes, skipping the usual star-forming phase entirely. Others suggest there could have been primordial black holes that were born in the very first moments after the Big Bang, rather than forming from dying stars. If that's true, it would mean that black holes have existed since the beginning of time itself, rewriting everything we thought we knew about how the universe evolved. The discovery of supermassive black holes in the early universe has left scientists scratching their heads. According to what we currently understand, black holes grow over billions of years by pulling in surrounding gas, dust, and even stars. But some black holes reached mind-boggling sizes, millions to billions of times the mass of our Sun, within just a few 100 million years after the Big Bang. This defies everything we know about how black holes evolve, suggesting that our theories about their formation and growth might be incomplete. The first galaxies were just beginning to form when these massive black holes appeared. In theory, black holes start small, forming from the collapse of massive stars, and then gradually grow larger over time. But if that were the case, how could some black holes have already reached such extreme sizes so soon after the universe began? It's like finding a fully grown tree in a place where seeds have only just been planted. Black holes grow by pulling in nearby material, gas, dust, and even stars. But in the early universe, there wasn't much of this material around yet. The first stars were only just beginning to form, and galaxies were still in their infancy. If black holes rely on consuming their surroundings to grow, how did some of them bulk up so quickly when there wasn't much to feed on? The way we currently understand black hole formation doesn't allow for such rapid growth. If black holes can indeed grow this fast, then there must be a process at work that we haven't discovered yet. Either black holes can somehow gain mass at an extreme rate that defies what we thought was possible, or there's a missing piece in our understanding of the early universe. Scientists have proposed several ideas to explain these early giant black holes, but none of them have been proven yet. Some theories suggest that instead of forming from collapsing stars, these black holes might have formed directly from massive clouds of gas collapsing under their own gravity, skipping the usual slow growth process. Others suggest that black holes may have merged rapidly in the chaotic early universe, accelerating their growth. Scientists have come up with a few interesting ideas to explain how these ancient supermassive black holes might have come into existence. One theory suggests that these early black holes didn't form from typical stars at all. Instead, enormous clouds of gas, some of them unimaginably vast, might have collapsed directly into black holes. This process could have bypassed the usual step of forming stars, allowing these black holes to begin as giant objects right from the start. By skipping the slow, gradual build-up, they could have been much bigger than the average black holes we see today. Normally, black holes grow by pulling in gas, dust, and other materials from their surroundings. However, there's a limit to how fast they can do this, known as the Eddington limit. This limit is based on the idea that as a black hole pulls in more and more matter, it starts to shine brighter due to radiation pressure. This pressure can counteract the black hole's gravity, making it harder for it to continue pulling in matter at an extremely fast rate. But some scientists believe that, in certain extreme conditions, black holes may have been able to defy this limit. They suggest that under very special circumstances, these black holes could have grown at a much faster pace than we ever imagined, possibly even outpacing the Eddington limit and becoming far more massive than we previously thought possible. Some scientists have come up with an intriguing idea. They think certain kinds of primordial black holes might have formed right after the Big Bang, the explosive event that created our universe. These black holes would have been formed during the very early moments of the universe's existence, and they could have been quite large right from the start. Because of their initial size, they would have had a huge advantage in growing bigger, quickly becoming what we now call supermassive black holes. It's a bit like starting a race with a head start, making it easier for them to grow faster than other black holes. Another theory suggests that black holes could have formed in groups rather than individually. These small black holes would have appeared in clusters, and as they moved closer to each other, they would have merged together. The merging process would have caused them to grow rapidly, so in a short period of time, these combined black holes could have turned into much larger ones, possibly even supermassive ones. In other words, a collection of smaller black holes could have combined so quickly that they reached enormous sizes far sooner than scientists would have expected. But perhaps the most intriguing idea is that these early supermassive black holes might be signaling that there's something important we don't yet understand about how the universe works. Some researchers think that solving this mystery could lead to groundbreaking discoveries in physics, like discovering unknown forces or even new types of matter that play a role in the growth of black holes. These discoveries could completely change our understanding of the cosmos. Scientists are excited to crack the mystery of the cosmos, and they believe new telescopes could be the answer. One of the most powerful tools they have is the James Webb Space Telescope, JWST, which is already peering deep into space, capturing stunning images of some of the universe's oldest galaxies. By studying these ancient galaxies and the black holes at their centers, astronomers hope to uncover the secrets of how these enormous structures came to exist so early in the universe's history. Each new image brings them closer to solving this cosmic puzzle, offering a glimpse into the past that could change everything we know about the universe's origins. The discovery of supermassive black holes in the early universe has left scientists scratching their heads, as it's one of the biggest mysteries of our time. These massive black holes shouldn't exist so soon after the Big Bang, yet here they are, defying everything we thought we knew about how black holes form. One thing is clear: Uncovering the truth behind these early supermassive black holes could lead to groundbreaking discoveries, possibly changing the laws of physics that have guided us for centuries. Until we find the answers, these cosmic giants will remain one of the most intriguing puzzles in the universe, waiting for the next breakthrough to reveal their true origins. One of the most fascinating mysteries of the universe is dark matter, an invisible substance that holds the cosmos together like an unseen web. Even though we can't see it with our eyes or detect it with traditional telescopes, scientists know it's there because of the way it influences the movement of galaxies and stars. Without dark matter, the universe as we know it wouldn't make sense. Unlike regular matter, which glows with the light of stars or reflects illumination, dark matter does neither. It doesn't emit, absorb, or bounce back any form of radiation, making it completely undetectable by normal means. That's why it's called dark, not because it's shadowy, but because it's hidden from our view. Yet its presence is undeniable. Scientists have observed galaxies rotating far too fast for the visible mass alone to hold them together. Something unseen is exerting an enormous gravitational pull, preventing them from flying apart. This unseen force is dark matter, and it has been silently shaping the universe since the beginning of time. Recent studies and technological advancements are bringing us closer than ever to uncovering its secrets, offering a glimpse into one of the greatest cosmic puzzles of all time. Imagine the universe as a giant puzzle, but most of its pieces are invisible. Scientists have discovered that everything we can see, stars, planets, and even ourselves, makes up only about 5% of the entire universe. That means all the galaxies, nebulae, and cosmic wonders we admire are just a tiny fraction of what's really out there. A much bigger portion, around 27%, is something called dark matter, a mysterious, unseen substance that doesn't emit light or energy, making it completely invisible to the human eye and even our most advanced telescopes. Yet despite being hidden, dark matter plays a crucial role in shaping the universe. It acts like a cosmic glue, holding galaxies together and preventing them from flying apart due to the immense speeds at which stars move. Without dark matter, galaxies, including our own Milky Way, wouldn't exist in their familiar spiral shapes. Instead, the stars would drift away into the void, and the universe would look vastly different. And then there's the biggest and strangest piece of all, dark energy, which makes up the remaining 68% of the universe. Unlike dark matter, which keeps galaxies intact, dark energy is doing the opposite. It's pushing the universe apart at an ever-increasing speed. Scientists still don't fully understand what dark energy is, but they know it's the driving force behind the universe's rapid expansion. So, in the grand scheme of things, the universe is mostly made of things we can't see or fully explain. Yet these invisible forces shape everything we know, from the tiniest atoms to the vast galaxies stretching across the cosmos. For many years, scientists have been trying to solve one of the biggest mysteries in the universe, the true nature of dark matter. They are certain it exists, not because they can see it directly, but because of the way it affects the movement of galaxies. When astronomers observe distant galaxies, they notice that they spin much faster than they should, given the amount of visible matter they contain. Something unseen, an invisible force, must be holding them together. That unseen force is what we call dark matter. To understand why dark matter is so crucial, we have to go back to the beginning of time itself, just moments after the Big Bang. The universe was a chaotic place, filled with hot plasma and energy, but as it began to expand and cool, dark matter played a key role in shaping what would become the vast cosmic structures we see today. It acted like an invisible framework, pulling gas and dust together to form the first galaxies, stars, and massive clusters of galaxies. Without it, the universe might have looked very different, perhaps too scattered for galaxies to even form. Yet, despite its fundamental role in shaping the cosmos, dark matter remains one of the greatest unsolved puzzles in science. What is it actually made of? Is it composed of undiscovered particles? Could it be linked to unknown forces beyond our current understanding of physics? Scientists have been searching for answers using massive underground detectors, powerful particle colliders, and even space telescopes. Every experiment brings us closer, but the truth still eludes us. The quest to uncover the secrets of dark matter is not just about answering a scientific question. It's about unlocking a deeper understanding of the universe itself. If we can solve this mystery, we may gain insights into how the universe began, how it evolved, and perhaps even discover new physics that could reshape everything we thought we knew. Scientists have recently made some exciting breakthroughs in their quest to understand dark matter, thanks to the use of highly advanced technology. Even though dark matter itself remains invisible, these discoveries are helping researchers piece together the puzzle of how the universe began and evolved. One of the most important clues comes from studying the cosmic microwave background, CMB, a faint glow of radiation left behind by the Big Bang. This ancient light serves as a kind of time capsule, allowing scientists to look back billions of years and see how the universe took shape. When scientists analyze the CMB, they notice tiny patterns or ripples in the radiation. These fluctuations reveal that dark matter must have been present early on, shaping the universe's first galaxies and other large structures. But how did dark matter do this if we can't see it? The answer lies in gravity. Although dark matter doesn't emit light or energy like stars and planets do, its gravity still affects ordinary matter. Scientists believe that the gravitational pull of dark matter helped draw regular matter together, forming the first galaxies and cosmic structures. Without it, the universe might look very different today. Right now, scientists are working on ways to detect dark matter directly. They are studying not only its indirect effects, like the way it influences galaxies, but also searching for particles or signals that might finally reveal what it's made of. Each new discovery brings us one step closer to unlocking one of the biggest mysteries in physics. In the beginning, the universe was a wild, chaotic place, bursting with intense energy and matter. Right after the Big Bang, everything was incredibly hot and dense, with particles speeding around in every direction. As the universe slowly cooled down, these particles began to stick together, forming the first atoms and basic structures. But this wasn't an easy process. Imagine the early universe as a giant boiling soup of particles. There had to be something to help organize this mess and bring some order. This is where dark matter plays a crucial role. Even though it's invisible, dark matter was already spreading out in massive amounts. As the universe continued to cool, dark matter began to clump together because of its strong gravitational pull. This clumping drew in regular matter, eventually helping to form the first galaxies and stars. Without dark matter's guiding hand, the universe might never have been able to create the vast galaxies and clusters of stars that we see today. Dark matter acted like a cosmic blueprint, shaping the way galaxies grew and organized themselves across the universe. One of the most intriguing things about dark matter is its ability to create dark matter halos. These halos are huge, invisible clouds of dark matter that wrap around galaxies, almost like an unseen protective shield. These halos are essential because they help hold galaxies together, stopping them from spinning apart into nothing. Scientists believe that every galaxy, including our very own Milky Way, is surrounded by such a halo. This discovery was a huge breakthrough in science. It not only proved that dark matter exists, but it also showed that it plays a crucial role in the way galaxies are formed and how they stay stable over time. Without these halos, galaxies might not be able to survive at all. One important clue about dark matter comes from a fascinating technique called gravitational lensing. This happens when the gravity of something really massive, like a galaxy or a group of galaxies, bends the light coming from objects that are located behind it. This bending of light creates a kind of cosmic magnifying glass, allowing scientists to see how mass is spread out across the universe, even when that mass is hidden from view. By studying how light bends in this way, scientists have been able to pinpoint where dark matter is located. The lensing effect reveals that there is a lot more mass in galaxy clusters than we can actually see with our eyes. This extra mass, which can't be detected directly because it's invisible, is believed to be dark matter. Even though we can't see it, dark matter still has an effect. It exerts a pull on light, bending it just like gravity bends space itself. This phenomenon is one of the most important pieces of the puzzle that could help us understand the mysterious nature of dark matter. Gravitational lensing has become one of the strongest pieces of evidence showing that dark matter exists. This phenomenon occurs when light from distant stars or galaxies passes through a massive galaxy cluster, and the gravity of that cluster bends the light, much like a magnifying glass. By studying how the light is distorted, scientists can figure out how much dark matter is hiding within these huge galaxy clusters. This method has helped us understand more clearly where and how dark matter is spread throughout the universe, painting a more detailed picture of its mysterious presence. Scientists are searching for clues about dark matter using different methods, such as studying gravitational lensing and the cosmic microwave background, CMB. These techniques help us spot signs of dark matter, but scientists are also on the hunt for the actual particles that make it up. Dark matter, in theory, is made of particles that barely interact with ordinary matter, which makes them extremely hard to find. These mysterious particles are known as WIMPs, weakly interacting massive particles. To catch a glimpse of WIMPs, scientists have set up various experiments, such as detectors deep underground and powerful particle colliders like the Large Hadron Collider, LHC. These experiments try to catch the moment when WIMPs might interact with normal matter. Despite many attempts, no one has directly detected dark matter particles yet, but the search is far from over. Each time an experiment fails to find them, it brings scientists a little closer to understanding the true nature of dark matter. Even the smallest discovery could be a huge leap forward in unraveling one of the greatest mysteries of the universe. Dark matter is one of the universe's most puzzling and important mysteries. While we can't see it with our eyes, we know it's there because of the way it affects everything around it. Through the study of distant galaxies, the cosmic microwave background, CMB, and gravitational lensing, where light is bent by unseen forces, scientists have gathered strong evidence that dark matter exists and plays a crucial role in shaping the universe. These discoveries not only help us understand what happened in the past, but also offer clues about what might happen in the future. As we uncover more about dark matter, we also learn about the basic forces that control everything in the universe. Dark matter is a key piece of the puzzle when it comes to understanding how galaxies were formed, how the universe has changed over time, and even what might happen to it in the end. It's possible that dark matter is connected to other mysterious forces like dark energy, which is driving the universe to expand faster and faster. By studying dark matter, scientists are hoping to uncover some of the biggest secrets about the universe, solving mysteries that could change our understanding of everything. The study of dark matter is far from finished. In fact, we're only beginning to uncover its mysteries. Scientists are constantly creating new tools and experiments to detect dark matter particles and understand its secrets. Over the next few decades, we might witness groundbreaking discoveries that change how we view the universe. New space missions like the James Webb Space Telescope are set to revolutionize our understanding of the cosmos. These missions will allow us to peer deeper into the universe than ever before, observing distant galaxies and cosmic events. By studying these far-off objects, scientists hope to uncover how dark matter shapes the vast structure of the universe itself. Meanwhile, here on Earth, more advanced detectors are being designed to find dark matter particles. These high-tech sensors are being placed in extreme locations, such as deep underground or even in space, where they will look for the faintest traces of dark matter's presence. With each new breakthrough, the mystery of dark matter inches closer to being solved. Dark matter is an invisible force that plays a huge role in shaping the universe, but we are only beginning to understand how it works. Recent discoveries have provided us with important clues about its presence and how it affects everything around us. While we can't actually see dark matter, we can feel its effects in the way galaxies, stars, and the whole structure of the universe are formed. Scientists are on an exciting quest to find dark matter particles and uncover their role in the cosmos. As they dig deeper, we will start to learn more about these mysterious forces that have been quietly shaping the universe since the very start of time. The journey to understand dark matter is just getting underway, and as the research moves forward, we can expect even more incredible discoveries to unfold. The discovery of the very first stars in the universe takes us on an exciting journey into the ancient past of the cosmos. These stars, called population 3 stars, are incredibly special because they were made up of only two elements, hydrogen and helium. They formed shortly after the Big Bang, at a time when the universe was still in its early chaotic stages. The James Webb Space Telescope, JWST, is playing a key role in studying these stars, allowing us to peek into a moment in time that happened billions of years ago, offering an unmatched view of the past. The The story of these ancient stars begins right after the Big Bang, an event that occurred around 13.8 billion years ago. The Big Bang was the moment the universe came into existence. In the first few minutes following this explosion, the universe was incredibly hot and dense, almost unimaginable to us today. At this stage, only the simplest elements could form: hydrogen, helium, and small amounts of lithium. Hydrogen, the simplest and most abundant element in the universe, was made up of single atoms, each containing just one proton in its core. Right behind it, helium, the second lightest element, had a slightly more complex structure with 2 protons and 2 neutrons. These 2 elements formed the very foundation of everything we see around us. However, at this stage, heavier elements like carbon, oxygen, and iron didn't exist yet. These essential building blocks for life would only appear much later through a process that unfolded in the hearts of stars. During this time, the universe was a dark and empty expanse, lacking stars, galaxies, or any bright points of light. This was an era of profound silence and darkness, known as the Cosmic Dark Ages, a period that stretched on for hundreds of millions of years. Yet, despite the stillness, an invisible force was at work. Gravity, slow but powerful, began pulling together the vast clouds of hydrogen and helium gas scattered across the void. As these clouds compressed under their own weight, they grew hotter and denser. Eventually, this sparked the birth of the first stars, lighting up the universe and breaking the darkness that had reigned for so long. The very first stars that appeared in the universe were completely different from the ones we see today. These stars were enormous, extremely hot, and mostly made up of hydrogen and helium, the 2 lightest elements. Astronomers call these stars population 3 stars to separate them from the stars that came later, which contain heavier elements. Population 3 stars played a critical role in shaping the universe. They were the first to light up the vast emptiness, sparking a major event in cosmic history called cosmic reionization. This process gradually turned the universe from being a dark, hazy place to one where light could finally travel freely. Before these stars formed, the universe was filled with neutral hydrogen gas that absorbed light, making it impossible to see anything. However, once population 3 stars began to shine, they released powerful ultraviolet radiation. This radiation ionized the surrounding hydrogen gas, meaning it stripped electrons from atoms, making the gas transparent. This transformation allows light to move across the universe, changing the way the cosmos looked forever. These stars were enormous, much bigger than our sun, often hundreds or even thousands of times its size. Their massive size meant that they burned through their fuel at a rapid pace, leading them to live very brief lives. While stars like our sun can exist for billions of years, these giants only lasted a few million years, a mere blink of an eye in the grand scale of the universe. When they finally reached the end of their lives, they didn't just fade away. They exploded in breathtaking supernovae, bursting with an incredible amount of energy. During these violent eruptions, they scattered heavy elements, like iron and gold, into the cosmos. These explosions played a crucial role in shaping the universe, providing the raw materials needed to form new stars, planets, and ultimately, the building blocks for life itself. The death of these massive stars wasn't just an end, but a creation story, marking the beginning of new worlds and everything that exists within them. Studying population 3 stars comes with one of the most difficult challenges in astronomy: their extreme faintness. These stars are incredibly distant, meaning the light they emit has to travel immense stretches of space before it finally reaches us here on Earth. Because of this, scientists rarely see these stars directly. Instead, they must hunt for indirect clues, like the effects these stars had on their environment. For instance, the light from population 3 stars might have been so powerful that it caused the gas surrounding them to become ionized. This is when atoms lose their electrons and turn into charged particles. This process could have created enormous bubbles of ionized hydrogen. By carefully analyzing the size and spread of these bubbles, scientists can uncover important details about the ancient stars responsible for forming them, giving us a deeper understanding of the universe's early history. The study of population 3 stars is not just a way to look back at the history of the universe. It also holds key insights into how life itself began. These ancient stars were the very first to create the heavy elements, like carbon, oxygen, and iron, that eventually formed planets. By examining these stars, we can uncover more about the conditions that allowed the first planets to take shape and, in time, gave rise to life as we know it. Population 3 stars are also crucial for understanding the big picture of how the universe evolved. These stars played a pivotal role in the birth of galaxies, black holes, and other cosmic structures. By studying their life cycles, from how they were born to their explosive deaths, we can piece together a clearer picture of the cosmic processes that have shaped the universe over the span of 13.8 billion years. Each discovery about these stars brings us one step closer to understanding the vast, intricate story of everything that exists in space. As the James Webb Space Telescope, JWST, continues its groundbreaking mission, it is set to uncover even more fascinating details about the early universe. Scientists are particularly eager to learn more about how the first stars and galaxies were born. These discoveries could shed light on how these early stars played a crucial role in shaping the vast universe we observe today. Looking ahead, upcoming telescopes and observatories will expand upon the incredible discoveries made by JWST. This will give astronomers a chance to collect even more information about these first stars. With advancements in technology, there is hope that one day we might even be able to detect the actual remnants of the very first stars, known as Population 3 stars. Finding these ancient stars would be like unlocking a time capsule, offering a direct connection to the earliest moments of the universe shortly after the Big Bang. The study of Population 3 stars is one of the most thrilling areas of modern astronomy. These stars, which formed in the very beginning of the universe, were made up only of hydrogen and helium. No other elements existed yet. They were key players in shaping the universe as we know it today. Thanks to the revolutionary technology of the James Webb Space Telescope, we now have the ability to look back in time and examine these stars in amazing detail like never before. This breakthrough allows us not only to learn more about the universe's past, but also to uncover the origins of the elements that make up everything we see around us today. The discovery of Population 3 stars promises to captivate and inspire scientists and astronomers for many years to come, as we continue to explore the mysteries of the universe's early stages and the birth of stars. Heavy elements are formed through a process called nucleosynthesis, where atomic nuclei fuse together in the hearts of stars. The heaviest elements are created during a special process known as the rapid neutron capture process, or R process, which happens when neutron stars collide or explode in powerful supernovas. Nucleosynthesis itself is the creation of new atomic nuclei from protons and neutrons, the building blocks of matter that already exist. According to scientists, the very first atomic nuclei formed just a few minutes after the Big Bang through a process called Big Bang nucleosynthesis. About 20 minutes after the Big Bang, the universe had expanded and cooled enough that high-energy collisions between particles slowed down. As a result, only the simplest reactions took place, leaving behind mainly hydrogen and helium, with small traces of other elements like lithium and deuterium, an isotope of hydrogen. Over time, stars and their explosions produced the vast array of elements we see in the universe today, a process known as cosmic chemical evolution. However, the universe still contains mostly hydrogen and helium, with heavier elements, or metals as astrophysicists call them, making up only a small fraction of the total mass. Stars are like giant factories where lighter elements fuse into heavier ones in their cores, releasing energy in the process. This is known as stellar nucleosynthesis. The fusion reactions create lighter elements, including iron and nickel in the most massive stars. The products of these fusion reactions are mostly trapped inside the stars unless they are ejected through stellar winds or explosions. Neutron capture reactions, like the R process and S process, help form even heavier elements, starting with iron and moving upwards. When a star explodes in a supernova, it produces even more elements, particularly those between oxygen and rubidium. This is due to the ejection of elements formed in earlier stellar processes, the intense explosive nucleosynthesis in the blast, and the R process that occurs when neutrons are rapidly absorbed during the explosion. A more recent discovery is that neutron star mergers, when two neutron stars collide, also create a significant amount of heavy elements through the R process. The collision releases a large amount of neutron-rich matter, which quickly forms new, heavier elements. Another process that creates elements is cosmic ray spallation. This happens when high-energy cosmic rays strike nuclei, breaking them apart. This process is a key source of lighter elements like helium-3, beryllium-9, and boron isotopes, which are not created by stellar nucleosynthesis. Cosmic ray spallation can take place in space, on asteroids, or even here on Earth in the atmosphere or soil, contributing to the cosmogenic nuclides found on our planet. On Earth, new atomic nuclei also form through radiogenesis, which occurs when long-lived ancient radioactive elements like uranium, thorium, and potassium-40 decay over time. Looking back to the Big Bang, it's believed that the very first building blocks of matter, protons and neutrons, formed from a superheated quark-gluon plasma about 13.8 billion years ago as the universe cooled. Within minutes, these particles came together to form the first atomic nuclei, including lithium and beryllium. However, elements like carbon couldn't form yet because the conditions weren't right, and the fusion process essentially stopped after about 20 minutes as the universe expanded and cooled further. This event, known as Big Bang nucleosynthesis, created the first primordial elements. Stars that formed in the early universe used these light elements, hydrogen, helium, lithium, beryllium, and boron, to build heavier elements. These light elements were leftovers from the Big Bang and cosmic ray spallation. Over millions of years, cosmic rays, mainly high-energy protons, caused heavier elements in interstellar gas and dust to break apart, creating new light elements like helium-3, lithium, beryllium, and boron. Carbon, which wasn't formed during the Big Bang, was created later in larger stars through a process called the triple alpha process, marking another milestone in the evolution of elements. The process of creating heavier elements requires extremely high temperatures and pressures, conditions found in stars and supernovae. This process began when hydrogen and helium, created by the Big Bang, collapsed into the first stars about 500 million years later. Since then, stars have continuously formed in galaxies. The earliest chemical elements, known as primordial nuclides, were produced by processes like Big Bang nucleosynthesis, stellar nucleosynthesis, supernova nucleosynthesis, and even in rare events like neutron-star collisions. Some elements, such as argon-40, were formed later through radioactive decay. Over time, Earth's mixing and evaporation have altered these original elements into what is now known as Earth's natural composition. The heavier elements, which appeared after the Big Bang, range from carbon to plutonium. These elements were created through nuclear reactions that involved the strong and weak forces between atomic nuclei, a process called nuclear fusion, which includes both rapid and slow neutron capture, along with nuclear fission and radioactive decay like beta decay. The stability of different atomic nuclei, based on the number of neutrons and protons, greatly influences how these reactions happen. That's why the study of cosmic nucleosynthesis is so important for researchers in astrophysics and nuclear physics, also known as nuclear astrophysics. Initially, scientists thought that all the chemical elements were created at the beginning of the universe, but no clear physical explanation could be found. Over time, it became clear that hydrogen and helium were much more abundant than any other elements. In fact, they make up almost everything in the universe, while all other elements together make up less than 2% of the mass in our solar system and others. Oxygen and carbon were found to be the next most common elements, and it was clear that lighter elements, especially those made of whole numbers of helium-4 nuclei, called alpha nuclides, were much more abundant. In 1920, Arthur Stanley Eddington first proposed that stars generate their energy by fusing hydrogen into helium and suggested that heavier elements might also form in stars. However, this idea wasn't widely accepted because the nuclear processes involved weren't fully understood. It wasn't until just before World War II that Hans Bethe explained how hydrogen fuses into helium through nuclear reactions. After the war, Fred Hoyle made significant contributions to understanding how heavier elements form in stars, explaining how all the elements heavier than hydrogen were created from it. Hoyle suggested that hydrogen is constantly created in the universe from vacuum and energy, without needing a beginning. His work also explained how the abundance of elements increases over time as the galaxy ages. This idea was expanded in the 1960s by researchers like William A. Fowler, Alistair G.W. Cameron, and Donald D. Clayton. A well-known paper in 1959 by E.M. Burbidge, G.R. Burbidge, Fowler and Hoyle summarized the field's progress, describing new processes for how heavy elements transform inside stars, processes that astronomers could study. The concept of the Big Bang itself was proposed in 1931 by Georges Lemaitre, a Belgian physicist, who suggested that the expanding universe must have started from a single point, a primeval atom. He theorized that if we traced the universe's expansion backward in time, it would eventually shrink to this point, before time and space even existed. Hoyle, in a 1949 BBC radio broadcast, coined the term Big Bang, although he denied it was meant to be insulting. He simply used it as a vivid image to contrast the Big Bang model with others. Lemaitre's theory was crucial in explaining the high amounts of helium and the existence of deuterium and other elements between helium and carbon, which were present not only in stars but also in interstellar space. In the end, both Lemaitre's and Hoyle's theories about how elements are created were essential for understanding the makeup of the universe. The theory of nucleosynthesis aims to explain why different chemical elements and their isotopes are found in varying amounts, all from the viewpoint of natural processes. A key reason this theory was developed comes from the strange patterns seen when the number of elements is graphed against their atomic number. When these abundances are plotted, the result looks like a jagged, saw-like line, with some elements being much more abundant than others, varying by factors as large as 10 million. One of the most important breakthroughs in this research was an abundance table created by scientists Hans Suess and Harold Urey. They based their table on the unchanged abundance of elements found in meteorites that hadn't gone through much transformation. This table, displayed on a logarithmic scale, visually smooths out the sharp spikes seen in the abundances due to the large range of values on the vertical axis. Various astrophysical processes are believed to be responsible for nucleosynthesis, with most of these taking place inside stars. The series of nuclear fusion processes in stars, known as hydrogen burning, can happen through two methods, the proton-proton chain or the CNO cycle. There are also stages of burning that follow: helium burning, carbon burning, neon burning, oxygen burning, and silicon burning. These fusion processes help create elements up to iron and nickel. This is the stage of nucleosynthesis where elements with the highest stability per nucleon are formed. For heavier elements, there are different processes involved. In stars, a neutron capture process known as the S process can form them, but in more extreme events like supernovae or the merging of neutron stars, other processes come into play. These include the R process, which happens when neutrons are rapidly captured, the RP process, and the P process, also called the gamma process, where existing nuclei are broken apart by high-energy photons. Stellar nucleosynthesis is the process that creates new atomic nuclei within stars. This happens during a star's life cycle and is key to understanding how elements from carbon to iron are spread throughout the galaxy. Stars act as massive nuclear furnaces where lighter elements like hydrogen, H, and helium, He, fuse together to form heavier elements as the star evolves. As the star's core becomes hotter and denser, fusion creates increasingly heavier elements. One of the most important elements in this process is carbon, which is produced through a series of reactions known as the triple alpha process. Carbon plays a crucial role because its creation marks a key step in the process of building heavier elements. In fact, carbon is responsible for releasing free neutrons inside stars, triggering the S process. This process slowly turns iron into even heavier elements like gold and uranium. After elements are formed in stars, they aren't kept inside the star forever. As stars age, they lose mass and expel these elements into space through stellar winds, especially in the later stages of a star's life. In smaller stars, this happens during the planetary nebula phase. In more massive stars, it happens at the end of their lives, when they explode in a supernova. These explosive events are responsible for sending large amounts of heavy elements into the universe. The first solid evidence that stars create these elements came when scientists observed that the interstellar gas from which new stars form became enriched with heavier elements over time. This meant that stars born later in the galaxy had much more heavy elements than earlier stars. In 1952, the discovery of technetium in the atmosphere of a red giant star provided even more proof of stellar nucleosynthesis. Technetium is a radioactive element, and because it decays quickly, It could only have been produced recently in that star, showing that nuclear reactions were happening inside it. More evidence came when astronomers found large amounts of barium in certain stars, specifically in stars on the asymptotic giant branch. The concentration of barium, much higher than in younger stars, suggests that the S process was at work in these older stars. Today, we have even more evidence from small particles called stardust, which are grains of material that come from individual stars. These grains are often found in meteorites and are called pre-solar grains because they formed before our sun existed. By studying these grains, scientists can learn about the processes that took place in the stars where they originated. The different isotopes found in stardust reveal key details about stellar nucleosynthesis and provide insight into how elements were created in stars during their final stages of life. Supernova nucleosynthesis happens in the intense, high-energy environment of a supernova. Here, elements between silicon and nickel are created through a process of rapid fusion, where nuclear reactions quickly bond with silicon-28 nuclei. This state, called quasi-equilibrium, can be thought of as almost stable, but with an abundance of silicon-28 in the fiery mix. This concept was a major breakthrough in the understanding of how intermediate elements, like those between silicon, atomic number 28, and nickel, atomic number 60, are made. It replaced an earlier idea from the B2FH paper that had incorrectly described the process and caused confusion, overshadowing earlier work by Fred Hoyle in 1954. The process doesn't stop there, though. In addition to the fusion happening in quasi-equilibrium, a rapid process known as the R process can occur, where elements heavier than nickel are formed by the rapid absorption of neutrons. This is a key part of the nucleosynthesis that happens during supernova explosions. The R process, first described by scientists Seeger, Fowler, and Clayton, can take place even in stars made only of hydrogen and helium, which was once thought to be impossible. It's responsible for the creation of many of the heaviest elements on the periodic table, such as uranium and thorium. However, scientists are still working to better understand how much of these elements are made in each supernova explosion. One of the most convincing proofs of the R process came from observations of ancient stars that were born in galaxies with low metallicity. These stars still contain R process elements, showing that the process happens inside stars and isn't dependent on the galaxy's overall metal content. There's also the RP process, or rapid proton process, which is similar to the R process, but involves the rapid absorption of protons along with neutrons. While its role in nucleosynthesis is still unclear, it may play a part in creating some elements. In the explosive conditions of a supernova, nuclei with equal numbers of protons and neutrons are formed rapidly, leading to many stable isotopes. This is because during the fusion of oxygen and silicon, nuclei with balanced numbers of protons and neutrons are created, producing elements up to nickel-60. The process forms stable isotopes like calcium-40, but heavier isotopes with equal protons and neutrons are unstable and decay after the explosion. This decay leaves behind more stable isotopes like iron-56, chromium-52, and titanium-48. The decay also releases gamma radiation, which scientists use to identify the elements created during the explosion. The discovery of gamma-ray lines from these decays was an important step in the field of gamma-ray astronomy, which helped to confirm explosive nucleosynthesis. One of the most striking pieces of evidence came from the 1987 supernova, where gamma-ray lines were detected coming from the explosion. These lines identified radioactive elements like cobalt-56 and cobalt-57, showing that the supernova had created these elements. This discovery confirmed the theory of explosive nucleosynthesis and was an important milestone in the development of nuclear astronomy. The data collected from these gamma-ray emissions were crucial in planning for NASA's Compton Gamma Ray Observatory. Another way we know that supernovae produce heavy elements is through the study of stardust grains. These grains form as the supernova expands and cools, and they are a key component of cosmic dust. Stardust grains contain isotopes like titanium-44, which was found to be abundant in the grains that formed during the supernova's explosion. This confirmed earlier predictions about the role of supernovae in creating stardust and helped scientists understand the specifics of explosive nucleosynthesis. The study of these unusual isotopic ratios in stardust grains continues to reveal important insights about how elements are made in these powerful stellar explosions. One of the most intriguing and mysterious parts of our universe are the giant gas clouds that float between galaxies. These clouds, made up of tiny bits of gas and dust, drift through the vastness of space, far away from stars or planets. They play a key role in helping scientists unlock the secrets of both the past and future of the universe, revealing how galaxies were born and how they might evolve in the years to come. Despite their importance, these clouds remain elusive and difficult to study, making them an even more exciting part of the cosmic puzzle. Intergalactic gas clouds are exactly what their name says, huge, wispy clouds of gas that float in the vast, empty space between galaxies. Unlike the bright, thick clouds of gas within galaxies that shine and swirl with energy, these clouds are much more spread out and diffuse. They're mostly made of hydrogen and helium, the two most common and simplest elements in the entire universe. These gas clouds can appear in many different forms. Some are freezing cold, barely moving, while others are blazing hot, full of energetic particles. There are also clouds that are actively shaping new stars, slowly gathering together and bursting into brilliant light. Because they are located in the vast stretches of space between galaxies, these clouds are hard to see directly with the naked eye. However, scientists can still spot them by observing the way they absorb or release light, revealing their presence in the otherwise empty cosmos. At the very beginning, right after the Big Bang, the universe was an incredibly hot and dense place. Imagine it like a giant boiling cauldron of gas swirling with immense energy. Everything was tightly packed together, and the universe was far from the calm, vast space we see today. As time passed, though, something amazing happened. The universe began to expand, stretching out in all directions. As it stretched, it also began to cool down, like steam from a pot of soup gradually slowing down and settling. As the universe cooled, the gas that filled it began to behave differently. Instead of staying in one dense mass, it started to break apart and group together in different ways. Some of this gas clumped together so tightly that it formed the first stars, giant balls of burning gas that shone brightly. These stars were the first beacons of light in an otherwise dark universe. And as these stars formed, they began to gather together, forming the first galaxies, vast collections of stars, gas, and dust, all held together by gravity. But not all of the gas turned into stars and galaxies. A large portion of it remained scattered across the universe, floating between galaxies in what scientists call the intergalactic medium. This space between galaxies is not empty, as it might seem, but is actually filled with a thin, hot gas. This gas is ancient. Some of it has been drifting through space since the early days of the universe. The study of these gas clouds is incredibly important because they hold secrets about the universe's past. By examining them, scientists can learn more about the early stages of the universe's evolution. These gas clouds are like time machines, allowing us to look back in time and understand what the universe was like long before we had stars and galaxies like the ones we see today. They give us clues about how stars formed, how galaxies took shape, and how the universe itself grew and changed over time. By studying these ancient clouds of gas, scientists can piece together a story about the universe's beginnings, giving us a deeper understanding of how everything came to be, from the very first moments after the Big Bang to the galaxies and stars we observe now. It's like reading the earliest chapters of a cosmic history book that tells us where we came from and how we got here. Intergalactic gas clouds are incredibly important when it comes to how the universe grows and changes. Without these clouds, we wouldn't have galaxies, stars, or even planets. These gas clouds aren't just random objects drifting through space. They're actually the raw materials that form everything we see in the cosmos. To really grasp how crucial they are, we need to dive into how these clouds work with galaxies and stars to shape the universe. Intergalactic gas clouds play a crucial role in one of the universe's most fascinating processes, the creation of stars. These clouds, mainly made of hydrogen gas, have the ability to collapse under their own gravitational pull. As this happens, the gas becomes more compressed and begins to heat up dramatically. When the temperature rises high enough, nuclear fusion starts, marking the moment a star is born. This entire process From the initial collapse of the gas cloud to the birth of a star can take millions of years. During this long stretch of time, the cloud undergoes incredible transformations, shifting from a cold, diffuse mass to a blazing, glowing ball of energy. While most stars form within the boundaries of galaxies, some gas clouds, known as intergalactic clouds, are able to collapse and create stars outside of these galaxies. These stars, often referred to as rogue stars, offer scientists a rare glimpse into the conditions that existed in the early universe, long before galaxies as we know them came into being. By studying how these distant clouds of gas collapse to form stars, researchers can uncover important details about the evolution of the universe. They can learn how the universe transformed over billions of years and gain a deeper understanding of the forces that shaped everything we see in the sky today. Gas clouds play a crucial role not just in the formation of stars, but also in shaping the growth and development of galaxies. Over long periods, galaxies expand by gathering gas from the space around them, including from vast clouds of gas that float between galaxies. This process, known as accretion, allows galaxies to grow bigger and bigger. The gas they collect doesn't just increase their size, it also sparks the creation of new stars, breathing fresh life into the galaxy. As galaxies grow, they don't just get bigger, they go through a series of changes. Some galaxies even collide and merge with others, creating much larger galaxies in the process. During these cosmic crashes, gas clouds from the different galaxies come into contact, causing dramatic bursts of star formation. These intense periods of activity help scientists uncover important clues about how galaxies evolve and how the vast and ever-changing universe continues to shape them over time. By observing how these gas clouds behave when they interact with galaxies, scientists gain deeper insights into the complex journey of galaxies from their beginnings to their present state and beyond, revealing the secrets of how galaxies grow and transform throughout the cosmos. Intergalactic gas clouds play a crucial role in the creation of heavier elements, a process that has been fundamental to the development of our universe. In the very beginning, only the simplest elements, hydrogen and helium, existed. But as time went on, stars began to form, and within their hot cores, a powerful process called nuclear fusion took place. This fusion allowed the stars to combine lighter elements like hydrogen to create heavier ones, such as carbon, oxygen, and iron. When these stars reached the end of their lives, many exploded in a brilliant event known as a supernova. These explosions scattered the newly formed heavy elements across space, seeding the surrounding gas clouds with these richer materials. Over millions and billions of years, the elements in these clouds mixed together, creating a more diverse range of elements. As new stars began to form from these enriched clouds, they were made up of a broader spectrum of elements, not just the lighter ones that existed in the early universe. This diversity of elements would go on to play a key role in the formation of planets, and eventually, life as we know it. By studying the makeup of these gas clouds, scientists can trace the journey of how elements formed and evolved in the universe. They are able to uncover a timeline of cosmic history, showing us how stars, explosions, and the mixing of elements helped shape the very universe we live in today. Studying gas clouds that stretch across galaxies is a tough challenge. These clouds are hard to see because they're very faint, spread out over vast areas, and usually hidden in parts of space that are tricky to observe. But thanks to new technology and improved methods, scientists have made huge strides in uncovering the secrets of these strange and distant clouds. Their discoveries are revealing more about the nature of the universe than ever before. To explore the mysterious intergalactic gas clouds scattered across the vastness of space, scientists rely on advanced telescopes that can pick up a wide range of light, beyond what the human eye can see. These clouds, unlike stars, don't shine with visible light. However, they interact with light in other ways, absorbing and emitting it across different wavelengths, like ultraviolet rays and radio waves. By studying these types of light, scientists can uncover important details about the gas clouds, such as their temperature, how dense they are, and what they're made of. A crucial tool in this investigation is the Hubble Space Telescope. This remarkable telescope has played a key role in observing distant parts of space, far beyond what we can see with the naked eye. One of Hubble's talents is its ability to detect faint light from objects like quasars, stars, and galaxies that are incredibly far away. As this light travels through intergalactic gas clouds, the clouds absorb specific wavelengths of the light. This creates a distinct fingerprint of light, which scientists can carefully analyze. By examining this unique pattern, researchers can figure out the cloud's characteristics, such as their chemical composition, temperature, and density, information that would be difficult to gather through any other means. Scientists use different types of telescopes to learn more about gas clouds in space. Along with optical telescopes like the famous Hubble, radio telescopes play a crucial role in this research. These special telescopes detect radio waves that are emitted by the gas within the clouds. Radio waves are unique because they can travel through thick dust and gas, which often block other types of light, like visible or infrared. This ability allows scientists to study parts of space that would be hard to see otherwise. A great example of a powerful radio telescope is the Atacama Large Millimeter Submillimeter Array, ALMA, located high in the Chilean Andes. ALMA is one of the most advanced radio telescopes in the world. It helps scientists observe cold, dense gas that is usually found in intergalactic clouds, which are regions between galaxies. By using ALMA and other radio telescopes, researchers can learn how gas clouds move, interact with each other, and change over time. This helps us understand the processes that shape galaxies, stars, and other celestial objects in space. In addition to using telescopes to observe gas clouds in space, scientists also rely on advanced computer simulations to study their behavior. These simulations let researchers recreate the conditions that existed in the early universe, allowing them to explore how gas clouds might have changed over billions of years. By comparing these simulated results with actual observations made through telescopes, scientists can test and refine their ideas about how galaxies, stars, and the universe itself came into existence. Simulations also help scientists make predictions about what might happen to gas clouds in the future. For instance, they can model how these clouds might collide with each other or interact with nearby galaxies. This helps scientists understand how galaxies might continue to grow or how new stars might form. These computer models are crucial for understanding how the universe has evolved over time and will continue to evolve in the distant future, offering insights into the mysterious processes that shape everything around us. One of the most fascinating parts of studying gas clouds that exist between galaxies is the way they offer a glimpse into the early days of the universe. These clouds are not just ordinary collections of gas. Some of them are billions of years old, which means when we observe them, it's almost like we're looking back in time to see how everything began. Think of them as time machines, bringing us closer to the origins of the universe itself. These intergalactic gas clouds are like ancient fossils, except instead of preserving bones or plants, they hold clues about the universe's conditions when it was still young and forming. They offer a snapshot of the early universe, a time before stars and galaxies were fully shaped. By studying these clouds, scientists can uncover secrets about the birth of the first stars and galaxies, how galaxies grew over time, and how the chemical elements we see today were first created. This knowledge is essential for piecing together the story of how our universe came to be, from its chaotic, fiery beginnings to the complex, star-filled universe we live in now. For instance, one of the key things scientists examine is the chemical makeup of these ancient clouds. The elements that make up stars, planets, and everything we know today were created in the earliest moments of the universe. By looking at the gases that existed in these clouds, scientists can trace how these elements formed and started to shape the universe's structure. In addition to studying the chemicals in these clouds, scientists also pay attention to how the gas clouds have interacted with galaxies over time. Galaxies are vast collections of stars, dust, and gas, and as time has passed, these clouds have been drawn into galaxies, playing a role in their growth and development. By understanding how these clouds have influenced galaxies, scientists can piece together how galaxies themselves have evolved from simple structures into the vast, intricate systems of stars. By comparing the gas clouds from the earliest times to those that formed later, scientists can also build a timeline of the universe's history. It's like comparing photographs taken at different stages of the same place over a long period of time, showing how it has changed and developed. This comparison helps scientists trace the universe's journey from its explosive birth, filled with hot, dense gas and energy, through the formation of the first stars, to the present-day universe with galaxies, stars, and planets in their current forms. Studying these ancient gas clouds is like unlocking a time capsule that reveals how everything we know about the universe came into being. Every piece of information we gather from them helps us understand how stars and galaxies were born, how they've grown and evolved, and how the elements that make up our world were formed. It's a fascinating journey back in time that allows us to better understand the universe's incredible story. Intergalactic gas clouds might appear to be just empty space at first glance, but in reality, they are far more than that. These vast clouds are packed with vital information that can help us unravel the mysteries of the universe, its past, present, and future. Far from being just empty space, these clouds play an essential role in the birth of stars and galaxies, and they also serve as time capsules, preserving the secrets of the ancient cosmos. As technology improves, the possibilities for discovering more about the intergalactic medium expand. These discoveries not only let us look back at the universe's origins, but also give us clues about its future. By studying these ancient gas clouds, we're doing more than just examining the past. We're learning how the universe will evolve, as we strive to answer some of the most profound and exciting questions about the cosmos and our place in it. For hundreds of years, people have gazed up at the stars, wondering if Earth is the only place in the universe with life. The night sky has always been a source of mystery, sparking endless questions about what might be out there. With billions of stars spread across the vastness of space, many have imagined that some of them could have planets similar to our own, worlds where life could exist. Scientists, astronomers, and dreamers have long speculated about the possibility of other Earth-like planets, but for most of human history there was no proof they existed. That all changed in recent decades. With incredibly powerful telescopes and ambitious space missions, we have now detected thousands of planets orbiting distant stars. These are called exoplanets. This discovery has completely transformed our understanding of the universe and our place in it. However, out of the thousands of exoplanets found so far, only a few seem to have the right conditions to support life as we know it. Even though the search is far from over, each new discovery brings us one step closer to answering one of humanity's biggest questions. Are we truly alone? Planets outside our solar system, known as exoplanets, orbit distant stars instead of our Sun. Some of them share similarities with Earth, making scientists wonder if they might support life. Others are massive gas giants like Jupiter, while some are so strange that they challenge our understanding of what planets can be. Astronomers have discovered exoplanets with extreme and bizarre conditions. Some are locked in eternal winter, covered in ice. Others are blazing hot worlds with oceans of molten lava. There are even exoplanets where it rains iron, as intense heat in their atmosphere turns metals into droplets that fall like fiery rain. The first confirmed exoplanets were discovered in 1992, orbiting a pulsar, a type of dead star that emits powerful beams of radiation. These planets were unlike anything in our solar system, proving that worlds could exist in places scientists never expected. Then, in 1995, astronomers found 51 Pegasi b, the first exoplanet orbiting a Sun-like star. This gas giant confirmed that planets existed around stars like our own, opening the door to an entirely new field of discovery. Since then, astronomers have identified over 5,005 exoplanets, and more are being found all the time. With advanced telescopes like the James Webb Space Telescope, scientists are now studying the atmospheres of these distant worlds, searching for signs of life and uncovering the secrets of planets beyond our solar system. Not all exoplanets are alike. Scientists group them into various categories depending on factors like their size, what they are made of, and where they are located within their star systems. Some of the most important types include gas giants are enormous planets, with two of the most famous examples being Jupiter and Saturn. These planets are made mostly of two simple gases, hydrogen and helium. Both gases are lighter than air and make up the majority of the planet's composition. Because of this, gas giants are incredibly massive, often many times larger than Earth. In fact, Jupiter is so big that over 1,300 Earths could fit inside it. These planets don't have a solid surface like Earth does. Instead, their outer layers are thick clouds of gas, and as you move deeper into the planet, the gas gets denser and hotter. Inside, the pressure is so extreme that hydrogen, which is normally a gas, turns into a liquid. At the very center of these gas giants, scientists believe there could be a solid core, but it's hard to know for sure because we can't send probes deep enough to confirm it. The reason we know so much about gas giants, especially those like Jupiter and Saturn in our own solar system, is because they're huge and shine brightly in the night sky. Their massive size makes them easier to spot, even with telescopes. These planets also give off more radiation than they receive from the sun, which makes them stand out more in space. Gas giants are common in the universe, and in fact, many of the exoplanets, planets outside our solar system, that scientists have discovered so far are also gas giants. This is mainly because of how easily they can be detected. When a gas giant passes in front of its star, it causes a noticeable dip in the star's light, a phenomenon known as a transit. This allows scientists to observe and study the planet from a great distance, even though it's far from us. While gas giants like Jupiter and Saturn are mostly made up of hydrogen and helium, some of the exoplanets discovered are even more unusual. For instance, some of these exoplanets may be hot Jupiters, which are gas giants that orbit their stars so closely that their temperatures soar to extreme levels. Others are ice giants like Uranus and Neptune, which, while still gaseous, contain more water, ammonia, and methane than Jupiter or Saturn. The discovery of so many gas giants, both near and far, has opened up a lot of exciting questions for scientists. What's the full range of conditions that these planets can exist in? How do they form? And could there be any form of life on planets with similar conditions to gas giants? Even though gas giants may seem inhospitable, their study can reveal a lot about how our universe works, how planets form, and what else might be out there in the vast stretches of space. Secondly, the Neptune-like planets, which are fascinating worlds that share some similarities with the planets Uranus and Neptune, both of which are located in our outer solar system. These Neptune-like planets are often called mini-Neptunes, because just like Uranus and Neptune, they are primarily made up of gases rather than solid rock or metals, but they are smaller than the massive gas giants like Jupiter and Saturn. To understand mini-Neptunes better, it helps to know a bit about the larger gas giants. Uranus and Neptune, for instance, are both known for their thick atmospheres made of hydrogen, helium, and various gases like methane. This composition gives them their striking blue color and results in very strong winds and intense weather systems. These planets also have icy components, as both of them are considered ice giants, a term that refers to the presence of water, ammonia, and methane ice within their atmospheres and interiors. Mini-Neptunes, though, are not as big as the gas giants like Jupiter. Jupiter, the largest planet in our solar system, is a massive ball of gas, but Neptune-like planets are much smaller in size and mass. Their smaller size means that they can have thick atmospheres composed mostly of hydrogen, helium, and ices, but they don't have the deep, dense cores of larger gas giants like Jupiter. This makes their atmospheres less thick, though still massive enough to be mostly gas. The defining feature of mini-Neptunes is that they often don't have the solid surface we might expect from planets like Earth or Mars. Instead, these planets are made up of a mixture of gases and ices, and in some cases they may have a rocky core at their center, though the core is often hard to study directly. In fact, some of these planets have been observed to have clouds, strong winds, and atmospheric systems that resemble those of Neptune and Uranus, making them look like smaller versions of their massive cousins. Astronomers are especially interested in these Neptune-like planets because they are relatively common in other star systems. Thousands of exoplanets, planets that orbit stars outside our solar system, have been discovered, and many of them are classified as mini-Neptunes. In fact, some studies suggest that mini-Neptunes could be among the most common types of planets in the galaxy. One of the things that make mini-Neptunes so interesting is the variety in their atmospheres and conditions. For example, some mini-Neptunes have thick clouds that trap heat, which could lead to very high temperatures on their surfaces. Others might have lighter atmospheres with more of a mix of gases and ices, which could allow for different kinds of weather patterns and atmospheric phenomena. Despite their similarities to Neptune, mini-Neptunes are still very different in other ways. Their size means they may not have the same strong magnetic fields or massive storm systems as their larger counterparts. However, they can still be very active worlds with fascinating weather and potentially even hidden oceans beneath their clouds. The discovery and study of these Neptune-like planets gives scientists clues about the conditions that might exist on other worlds, and even help us learn more about the formation and evolution of planets in general. In the future, as technology advances, we may be able to learn even more about these mysterious planets, potentially uncovering details about their atmospheres, weather systems, and even the possibility of life. With new space missions, scientists hope to send probes to study planets like these up close, uncovering their secrets and expanding our understanding of the universe. Then comes super-Earths, which are fascinating planets that fall between the size of Earth and Neptune. They are much bigger than our home planet, but they don't reach the enormous size of gas giants like Neptune or Jupiter. The term super-Earth only refers to their size and mass, not what they are made of or whether they can actually support life. Some of these planets might have solid rocky surfaces, similar to Earth, while others could be covered in thick layers of gas or ice. One of the most exciting things about super-Earths is that some of them could have the right conditions for life. Scientists believe that if a super-Earth orbits its star at the right distance, where temperatures are not too hot and not too cold, there could be liquid water on its surface. Since water is essential for life as we know it, these planets could potentially host living organisms, from tiny microbes to more complex life forms. Another interesting feature of super-Earths is their strong gravity. Because they have more mass than Earth, their gravity would be much stronger. This means that if humans were to land on one, they might feel much heavier and find it harder to move around. However, a strong atmosphere could also provide better protection against harmful space radiation, making some of these planets even more suitable for life. Super-Earths come in many different types. Some may be covered in vast oceans that stretch across the entire planet. Others might have thick clouds and a dense atmosphere, trapping heat and creating conditions similar to Venus. Some could be rich in valuable minerals or even have unique chemical compositions that we have never seen before. Because they are bigger than Earth, these planets could have a more active core, leading to strong volcanic activity. This could help create a stable atmosphere by releasing gases over millions of years. If a super-Earth has a magnetic field, like Earth does, it could also protect the planet from harmful solar winds, making it even more Earth-like. Astronomers have already discovered many super-Earths in distant star systems, and new telescopes are helping scientists study them more closely. Some of the most famous ones, like Kepler 22b and TOI 700d, have sparked excitement because they seem to be in the habitable zone of their stars, where conditions might be right for life. Terrestrial planets are the rocky planets in our solar system that include Earth, Mars, Venus, and Mercury. These planets are unique because they are made mostly of solid rock and metal, giving them a hard, stable surface. This is quite different from the gas giants like Jupiter and Saturn, which are mostly made of gas and don't have a solid surface that we could stand on. The solid nature of terrestrial planets makes them especially interesting to scientists who are searching for planets that could support life. Earth is the most well-known of the terrestrial planets because it is the only one known to have life. Scientists are constantly looking for other planets that might be similar to Earth, hoping to find another place in the universe where life could exist. This has made planets like Mars, Venus, and Mercury extremely fascinating for space researchers. Mars, for example, has been a key focus for scientists because it has a rocky surface with signs of ancient rivers and lakes. Some researchers believe that Mars might have had the right conditions for life in the past, and they're eager to learn more about its history. NASA has sent multiple rovers to Mars to explore its surface and gather information that could tell us whether life ever existed there. Venus is another terrestrial planet that catches the attention of scientists, though in a very different way. It is often called Earth's twin because it is similar in size and structure. However, Venus is incredibly hot and covered in thick clouds of toxic gases, making it a very hostile place for life as we know it. Despite this, scientists are still intrigued by Venus because studying its extreme conditions could help us understand more about how planets evolve and why Venus turned out to be so different from Earth. Mercury, the smallest of the terrestrial planets, is another fascinating object of study. It is closest to the Sun, so it experiences extreme temperatures, extremely hot during the day and freezing cold at night. Scientists are curious about how Mercury formed and how its surface has changed over billions of years. Its lack of atmosphere makes it an ideal place for studying impacts from space debris. The common thread among these planets is that they all have solid surfaces, which makes them unique in the solar system. Scientists are especially focused on finding other rocky planets outside our solar system, in a region called the habitable zone. This is the area around a star where conditions might be right for liquid water to exist, which is essential for life as we know it. Terrestrial planets are not just fascinating because of their solid rock surfaces, but because they provide clues about the possibility of life on other worlds. Scientists continue to study Earth's neighbors and beyond, hoping to uncover the secrets of these intriguing planets. Not every planet is capable of supporting life. For a planet to be livable, it needs the perfect conditions to allow liquid water to exist. But why is water so crucial? Well, every living thing we know of, whether it's tiny bacteria, towering plants, or animals like ourselves, relies on water in some way. Scientists think that if a planet has liquid water, it stands a much better chance of hosting life. Several important factors help scientists figure out if an exoplanet might be able to support life. The habitable zone, often referred to as the Goldilocks zone, is a special region around a star where a planet is at just the right distance to support life. Think of it like the perfect spot in the universe, where things aren't too hot or too cold, but just right for life to thrive, particularly because liquid water can exist. This zone is crucial because water, as we know, is essential for life. If a planet is too close to its star, like Venus, it becomes unbearably hot. The temperatures rise so much that any water on the planet would instantly evaporate into the air, leaving the surface dry and uninhabitable. It's like being too close to a fire. Everything would burn up. On the other hand, if a planet is too far from its star, like Mars, it becomes too cold. The chill is so intense that water would freeze, turning into ice, and making it impossible for liquid water to exist on the surface. Imagine being so far from the warmth of the sun that everything is frozen solid, a lifeless, frozen world. However, Earth finds itself in the sweet spot, perfectly positioned within the habitable zone. It's not too close and not too far from the sun. This ideal distance allows Earth to support liquid water, which forms lakes, rivers, oceans, and even the clouds in the sky. These bodies of water are vital for all forms of life on Earth, providing a source of nourishment, transportation, and a habitat for countless species. Because of this unique position, Earth is a rare gem in the universe, a planet teeming with life, where water flows freely, and the conditions are just right for organisms to survive and flourish. In essence, the habitable zone is like the Goldilocks story. Everything is perfectly balanced, offering the ideal environment for life to thrive. It's a place where water can flow, temperatures are moderate, and life, as we know it, has the chance to grow. Without this zone, Earth would either be a blazing hot inferno or a frozen wasteland, both of which would make life impossible. Earth's spot in this zone is one of the reasons why it is so special and unique in the vastness of space. A planet's atmosphere acts like a cozy, protective blanket that surrounds it, offering much-needed protection and balance. Imagine it as a shield, one that keeps the planet safe from the harsh, unforgiving environment of space. This blanket helps trap warmth from the sun, ensuring that the temperature on the planet is neither too cold nor too hot. Without this shield, a planet's surface could swing from extremely freezing temperatures at night to scorching heat during the day, making life nearly impossible. On Earth, our atmosphere is made up of several important gases, with oxygen being one of the most vital. Oxygen is the gas we breathe in, allowing us to live and thrive. But oxygen isn't the only gas that makes Earth's atmosphere so special. There's also carbon dioxide, which plays a crucial role in keeping the planet warm. Carbon dioxide traps heat in the atmosphere, a process known as the greenhouse effect, which is necessary to maintain Earth's warmth. Without enough of this gas, our planet could become too cold to support life. But if there were too much carbon dioxide, it could cause the planet to overheat. The right balance is essential. Now consider the moon. Unlike Earth, the moon has no atmosphere. This means there's nothing to protect it from the harshness of space. During the day, the temperature on the moon can rise to over 250 degrees Fahrenheit, while at night, it can drop to a bone-chilling -280 degrees Fahrenheit. Without an atmosphere to regulate the temperature or shield the surface from dangerous solar radiation, life as we know it is impossible there. In contrast, Venus has a very thick atmosphere made mostly of toxic gases like carbon dioxide. This creates a runaway greenhouse effect, where heat is trapped so effectively that the temperature on Venus is around 900 degrees Fahrenheit, hotter than an oven on the highest setting. This extreme heat, along with the poisonous gases in the air, makes Venus a place where life cannot survive. A planet needs the right type of atmosphere to support life. It has to have the right balance of gases to keep temperatures stable and protect the surface from harmful space radiation. Too little atmosphere, and the planet will freeze. Too much, and it will burn. Earth is unique in having the perfect combination for life to flourish. The Earth is unique in many ways, but one of the most important features that makes life possible here is its magnetic field. This magnetic field acts like a giant shield, protecting us from the harmful radiation coming from the sun. The sun constantly sends out powerful waves of energy, known as solar radiation. Without Earth's magnetic field, these rays would hit our planet directly, and over time, they could slowly strip away our atmosphere. Why is this so important? Well, our atmosphere is what keeps us alive. It's made up of gases that we breathe, like oxygen and nitrogen, and it also helps regulate the temperature on Earth, keeping it just right for life. If the sun's radiation could tear our atmosphere away, there would be no air to breathe, no protection from the heat of the sun, and no way for life to survive. It would be like living in an endless, frozen desert. Now let's think about what happened to Mars. Unlike Earth, Mars lost its magnetic field a long time ago. This means that there is no shield to protect it from solar radiation. Over millions of years, the sun's rays slowly began to strip away the Martian atmosphere. Today, Mars has a very thin atmosphere, which isn't able to keep in heat or protect the surface. As a result, the surface of Mars is dry, cold, and barren. There are no oceans, no forests, and no life. Scientists believe that Mars might have once had a thicker atmosphere, and it may have been more Earth-like, with flowing water and perhaps even some form of life. But without a magnetic field to protect it, the sun's radiation took its toll, leaving Mars the cold and desolate planet we see today. So, the magnetic field on Earth isn't just a random feature, it's a life-saving shield. It's one of the reasons Earth is so special in the vastness of space. Without it, our planet might have faced the same fate as Mars, becoming a lifeless, inhospitable place where survival would be impossible. Even though a planet is located in the habitable zone, which means it's at just the right distance from its star to possibly support life, there's still something essential it needs: liquid water. You see, water is the foundation for life as we know it, and while frozen water might exist on some exoplanets, planets that orbit stars outside our solar system, it isn't enough on its own. For life to thrive, water must be in liquid form. This is because liquid water is the perfect environment for chemical reactions, which are necessary for life to develop and continue. Think about Earth. Without oceans, lakes, or rivers, life would have a much harder time surviving. So, when scientists study exoplanets, they focus on finding clues that could indicate the presence of liquid water. This could be in the form of large bodies of water like oceans, or perhaps rivers and lakes. In some cases, there might even be underground water hidden beneath the surface that could support life in a completely different way. The search for these signs isn't simple, though. Scientists use powerful telescopes and complex technology to detect exoplanets and analyze their atmospheres, looking for hints that water might exist. They search for the right temperatures and conditions that would allow water to remain liquid, not frozen or vaporized. It's a delicate balance because a planet too close to its star could have water vaporized into gas, while one too far might have it frozen solid. These efforts to find liquid water on other planets are critical because they give scientists the best chance of finding life beyond Earth. Not every star is capable of supporting planets where life could exist. Stars come in all sizes, and their size plays a crucial role in determining whether or not they can have habitable planets orbiting them. Some stars are very big, much larger than our own sun. These giant stars burn incredibly hot and fast, using up their fuel much quicker than smaller stars. They shine brightly for a short period of time, But this rapid burning process means that any planet orbiting them would only have a limited window of time before the star exhausts its fuel and dies. This short lifespan is not ideal for life to develop and thrive. On the other hand, there are smaller, cooler stars. These stars burn much slower and live for a very long time, but because they are not as hot, they may not provide enough warmth for planets that orbit them. A planet too far away from one of these stars might not receive enough energy to maintain liquid water, which is considered one of the key ingredients for life as we know it. Without the right amount of warmth, these planets would likely be too cold to support life. The stars that seem to be the best candidates for hosting habitable planets are the ones that are similar in size to our Sun. These Sun-like stars have just the right balance of heat and stability. They shine steadily for billions of years, providing a consistent source of energy for any planets orbiting them. This stability gives life the time it needs to develop and evolve. However, even stars that are a little smaller than our Sun, known as K-dwarfs, are also good candidates for hosting habitable planets. While these stars are slightly cooler, they still have a stable output of energy and a very long lifespan, making them ideal for sustaining life over extended periods. These stars burn their fuel at a slower rate, allowing them to shine for tens of billions of years, much longer than our Sun will. In short, for a planet to have the right conditions for life, the star it orbits must provide a stable and consistent source of energy. Stars that are too big burn out too quickly, while those that are too small may not offer enough warmth. The best candidates are stars like our Sun or slightly smaller K-dwarfs, which strike the perfect balance between heat, stability, and longevity. Exoplanets are incredibly far from Earth, so scientists can't actually see most of them with their eyes. Instead, they use clever methods to figure out that these distant planets are out there. By studying how light behaves or observing how the stars move, they can uncover the hidden secrets of these faraway worlds. These techniques allow scientists to detect planets that we may never be able to see directly, giving us a glimpse into the vastness of space. The transit method is one of the most widely used ways that scientists detect planets beyond our solar system, called exoplanets. It's like watching a tiny shadow pass across a bright light. Here's how it works. Scientists begin by closely observing a star, which is far away in space. This star is often hundreds or even thousands of light years away from Earth. Now, stars shine very brightly, so when a planet moves in front of one, it causes a slight but noticeable change in the star's brightness. Imagine the planet as a small, moving object that briefly blocks out a little bit of the star's light as it crosses in front of it. This dimming of the star is very subtle, but it happens regularly, depending on how often the planet orbits around the star. The amount of light that gets blocked depends on the size of the planet and how much of the star it covers as it moves. Scientists can then detect this small and regular drop in light by carefully tracking the star over time. When they see this kind of pattern, where the star dims and brightens at consistent intervals, they know that something is causing it. That something is likely a planet passing in front of the star. By measuring how much the light dims, scientists can even learn about the size of the planet. Larger planets block more light while smaller ones block less. The Kepler Space Telescope, which was launched by NASA, is one of the main tools used to find planets using this method. Kepler has been scanning the sky for years, watching the light from thousands of stars. Thanks to its observations, Kepler has discovered thousands of exoplanets that we would have never known about otherwise. Each of these planets is orbiting its own star, many in distant parts of our galaxy. By using the transit method, scientists are not only finding new planets but also gaining valuable information about them, such as how long it takes for the planet to complete its orbit and whether the planet might be in the habitable zone, a region around a star where conditions could be right for life. This method is so effective that it has led to some of the most exciting discoveries in the search for life beyond Earth. When a planet's transit is detected, scientists can follow up with other instruments to learn even more, like whether the planet has an atmosphere or if it's made of rock, gas, or ice. Every time a planet passes in front of its star, it gives scientists a clue that leads to the discovery of new distant worlds. The radial velocity method, also known as the wobble method, is a fascinating way scientists find planets that are far away from us, even when we can't see them directly. Here's how it works. When a planet orbits around a star, its gravity pulls on the star ever so slightly. Think of it like a tug of war. While the planet is moving in its orbit, it exerts a small force on the star, causing the star to move or wobble just a little bit. Now, this wobble is incredibly small, so small that you wouldn't notice it with the naked eye, but it's there. Stars are massive, but they don't just stay in one place. Even though they appear to be stationary, they're actually moving in response to the planets orbiting around them. This movement is due to the gravitational pull the planet exerts as it moves in its orbit. So, while a planet is pulling on the star is moving in a tiny circle or ellipse in response to this pull. To detect this wobble, scientists use very sensitive instruments that can measure the star's movement with extraordinary precision. By observing the star's position in the sky and tracking how its light shifts, they can detect the tiniest wobble caused by an unseen planet. These shifts in light happen because of something called the Doppler effect. This effect is the same reason why a car engine's sound changes as it drives past you. When the star moves toward us, the light gets slightly bluer, a shift to shorter wavelengths. When it moves away, the light becomes redder, a shift to longer wavelengths. By measuring these small color shifts, scientists can tell if a planet is tugging on the star. Now imagine trying to detect a planet that is millions or even billions of light years away. Without seeing the planet itself, the wobble method allows scientists to know it's there. This method works for planets that might be too far to see directly, or even planets that are too faint compared to their stars to spot through a telescope. The beauty of the radial velocity method is that it lets us learn about planets that we wouldn't be able to detect otherwise. We can figure out things like the planet's mass, how far it is from its star, and sometimes even how strong the gravitational pull between the two is. It's like uncovering hidden information about a planet without ever seeing it. This method has been crucial in finding many exoplanets, planets that orbit stars outside our solar system. In fact, it has helped astronomers discover hundreds, if not thousands, of planets we didn't know existed. And the best part? It opens up a window into the vast, mysterious universe, giving us clues about other worlds that might one day be explored. The radial velocity method allows scientists to detect hidden planets by measuring how their gravity causes their stars to wobble. The direct imaging method is an exciting and rare technique that allows scientists to capture real pictures of exoplanets. Exoplanets are planets that exist outside of our solar system, orbiting stars far away. But here's the challenge. Stars are incredibly bright, and their light can make it nearly impossible to see the faint and distant planets orbiting them. It's like trying to spot a tiny, dim light in the middle of a huge spotlight. To overcome this problem, scientists use highly advanced telescopes that have special technology. This technology is designed to block out the overwhelming light from the star, allowing the telescope to focus on the much dimmer exoplanet. It's almost like using a pair of special glasses that help you see the faintest details in the dark, even with a blinding light in the background. While this method is not something scientists can do every day, it is incredibly valuable when it works. It provides the rare opportunity to directly observe exoplanets, helping us understand their size, atmosphere, and even the conditions on their surface. With these images, researchers can learn more about whether these exoplanets could support life, or if they have any similar features to the planets in our own solar system. Direct imaging allows scientists to take a snapshot of distant worlds, bringing us closer to understanding the vast and mysterious universe around us. The gravitational microlensing method is a fascinating and powerful technique used by astronomers to find planets in space that would be impossible to detect using traditional methods. To understand how it works, let's break it down. Imagine a planet drifting in the vastness of space. Now picture a distant star shining light billions of miles away. Normally, the star's light travels straight toward us, but if the planet happens to pass directly in front of that star, something incredible happens. The gravity of the planet acts like a magnifying glass, bending the light from the star in a way that makes the star appear brighter and bigger than it really is. This bending of light occurs because gravity has a unique ability to warp the space around it, according to Einstein's theory of relativity. The more massive an object, like a planet or a star, the stronger its gravitational pull. When the planet moves in front of a distant star, its gravity distorts the star's light path. This phenomenon creates a temporary and noticeable brightening effect, which is what we call microlensing. What makes this method so special is that it can reveal planets that we can't see with regular telescopes. These planets could be far away, in places where no light is coming directly from them. Typically, detecting a planet involves spotting the light they reflect, or detecting the small gravitational pull they exert on their parent star. But in some cases, these methods don't work, especially if the planet is too small or too far from its star. However, with gravitational microlensing, even the smallest and most distant planets can be detected as long as they pass in front of a star. This rare event is a bit like finding a hidden treasure in space. The moment the planet's gravity bends the light, scientists on Earth can use special instruments to measure the change in the light's brightness. They can then study this change to figure out details about the planet, like its size, location, and even how far it is from its star. Gravitational microlensing is not only a way to detect planets, but it also helps scientists study other objects in space, like black holes or other strange cosmic phenomena that could also cause similar light bending. Because the planets detected this way are often in faraway parts of the universe, the method opens up an entirely new way to explore and understand space, allowing astronomers to discover things they couldn't have dreamed of just a few decades ago. Astronomers have discovered a number of exoplanets that might be capable of supporting life, and each one has unique characteristics that make them fascinating to study. Some of the most exciting of these planets include Proxima b. This planet orbits Proxima Centauri, the closest star to our solar system, located just over 4 light-years away. Proxima b is situated within the habitable zone, an area where conditions might be right for liquid water to exist on its surface. While this is a hopeful sign, scientists are still investigating whether the planet has a protective atmosphere that could make it possible to sustain life. TRAPPIST-1 System. A remarkable star system located about 40 light-years away, it contains 7 planets roughly the size of Earth. 3 of these planets are in the habitable zone, where temperatures could allow liquid water to exist. This makes TRAPPIST-1 one of the most promising systems for the search for alien life, with scientists paying close attention to its potential. Kepler 442b, known as a super-Earth, Kepler 442b is a planet that lies within the habitable zone of its star. It's around 1,200 light-years away, but it's considered one of the best candidates for habitability. Its size and location suggest that it might have the right conditions, such as the right temperature and an atmosphere, for life to thrive. LHS 1140b, a rocky planet about 40 light-years away, LHS 1140b is another exciting find. It's believed to have a thick atmosphere and possibly even liquid water, making it an excellent candidate for scientists who are looking for signs of life beyond our solar system. Its rocky surface also suggests it could have Earth-like conditions. These planets are just a few examples of the many exoplanets scientists are studying. Each discovery brings us closer to understanding whether life could exist elsewhere in the universe, making these distant worlds incredibly intriguing. With powerful telescopes like the James Webb Space Telescope, JWST, scientists now have an incredible tool to explore the atmospheres of planets outside our solar system, known as exoplanets. They carefully examine these distant worlds, searching for specific gases such as oxygen, methane, and carbon dioxide. These gases are important because on Earth they are closely linked to life. For example, oxygen comes from plants, methane is often produced by living organisms, and carbon dioxide is a key part of the cycle of life. Even though scientists haven't yet found direct proof of alien life, the discovery of thousands of planets that could potentially support life has made the search more exciting than ever. The sheer number of these planets suggests that life might not be unique to Earth. Somewhere out there, in the vastness of the universe, another world might be teeming with life, waiting to be discovered. A biosignature, also known as a chemical fossil or molecular fossil, is any substance, such as an element, molecule, or specific pattern, that serves as proof of life, whether past or present on a planet. These clues can come in many forms, including unique chemical compositions, physical structures, or even unusual atmospheric changes that suggest biological activity. Scientists in astrobiology, the study of life in the universe, rely on biosignatures to search for signs of life beyond Earth. The presence of certain gases, organic materials, or specific patterns in rock formations could hint at alien life, whether microbial or even advanced civilizations. Biosignatures can be grouped into 10 major categories, each providing different kinds of evidence for life. Isotope patterns. Living organisms process elements like carbon or oxygen in distinct ways, leaving behind unique isotope ratios that don't typically occur through non-biological processes. Chemical signatures. Certain chemical compounds like oxygen and methane appearing together strongly suggest biological activity. Organic matter life forms produce organic molecules like proteins, fats, and carbohydrates, which can be preserved in rocks or sediments. Biological minerals. Some organisms create minerals in ways that are different from geological processes, like magnetite crystals found in bacteria. Microscopic structures. Tiny textures and patterns, such as microfossils or bacterial films, that indicate biological activity. Macroscopic structures. Large-scale formations, such as fossilized coral reefs or layered rock formations like stromatolites, which are created by ancient microbial communities. Changes over time. If a planet's atmosphere or surface reflectivity changes periodically, it could indicate biological cycles, like plants affecting oxygen levels. Surface reflectance features. Some life forms produce pigments that change how light reflects off a surface, which could be detected from space. Atmospheric gases. Certain gases, like oxygen and methane, are often produced by life and can accumulate in a planet's atmosphere. Technosignatures. Signs of advanced civilizations, such as artificial lights, radio signals, or pollution, which wouldn't occur naturally. Not everything that looks like a sign of life actually is. For something to be a strong biosignature, it must meet 3 key criteria. Reliability. It must be clearly linked to life rather than non-biological processes. Survivability. It must be stable enough to last long enough to be detected. Detectability. Scientists must be able to find and measure it accurately. A big challenge is that non-living processes like volcanoes or chemical reactions in rocks can sometimes create similar effects to biosignatures. Scientists must carefully rule out other possible explanations before concluding that life is the cause. One way they do this is by looking for geochemical imbalances, situations where certain elements or compounds exist in unusual amounts or combinations. For example, if a planet has both methane and oxygen in its atmosphere, it suggests something is constantly replenishing them, since these gases would naturally react and cancel each other out over time. That imbalance might be a strong clue pointing to life. For a biosignature to be useful, it has to remain detectable for a long enough time that it can be found by probes, telescopes, or even humans. One of the byproducts of life is metabolic waste, which is created when organisms use energy through chemical reactions. Additionally, the physical remains of organisms like fossils can be preserved over time, with some fossils on Earth dating back as far as 3.5 billion years. These byproducts and remains can serve as strong evidence of life because they directly show that life once existed. However, for a biosignature to work as proof of life, it has to stay intact long enough for scientists to detect it. A biosignature must also be detectable with the most advanced technology available to be useful in scientific studies. This may seem obvious, but there are many situations where life could exist on another planet and still go unnoticed due to the limitations of human technology. Each potential biosignature comes with its own set of challenges, as certain natural processes might mimic the signature of life. Take oxygen, for example. On Earth, oxygen is mainly produced by photosynthesis, which is a process carried out by plants and other life forms. Oxygen is also crucial for many organisms to breathe. It's easy to detect in a planet's atmosphere because it shows up in distinct patterns of light across a wide range of wavelengths, making it a great candidate for a biosignature. But finding oxygen alone doesn't prove there's life because there are other non-living processes that could also create oxygen. For instance, oxygen could form through a natural process called photolysis, especially if the planet has lost a lot of water or has very few gases that can't condense. Figuring out whether a potential biosignature is truly a sign of life or just a result of natural processes is one of the most difficult challenges scientists face. It requires creativity and deep understanding to separate biological signals from abiotic, non-living ones. On the flip side, there's the issue of false negatives, situations where life might actually be present on another planet, but certain factors make the signs of life undetectable. This is a significant problem that scientists are actively studying as they prepare for future telescopes that will be able to examine the atmospheres of exoplanets. Humans also face several challenges in detecting biosignatures. One of these is the resolution of the telescopes we use. If telescopes aren't powerful enough, they may not be able to detect the subtle features of biosignatures, especially when trying to rule out false positives. Furthermore, telescopes and probes are built by large teams of scientists with different goals. Because of this, these instruments often have to strike a balance between various research interests, which means they may have to compromise on the ability to search for certain biosignatures in favor of studying other phenomena. This compromises the capability to search specifically for signs of life. The Earth's ancient history offers us a chance to understand the kinds of chemical traces that life forms, especially microbes, leave behind, and how these traces are preserved in rocks and sediments over millions of years. Several fields like geochemistry, geobiology, and geomicrobiology focus on studying these traces, called biosignatures, to figure out whether life ever existed in a sample. Some of the key types of biosignatures include microfossils and stromatolites, layers of sediment created by microbial life, molecular markers, biomarkers, and the specific isotopic makeup of elements like carbon, nitrogen, and hydrogen found in organic materials, various sulfur and oxygen isotopes found in minerals, and patterns in the abundance and isotopic makeup of metals that change in response to environmental conditions, like iron, molybdenum, chromium, and rare earth elements. For instance, the types of fatty acids in a sample can reveal which bacteria and archaea are thriving there. Another example is the long-chain fatty alcohols, which are produced by planktonic bacteria and have more than 23 carbon atoms. Geochemists often refer to these markers as biomarkers. Also, the presence of certain straight-chain lipids like alkanes, alcohols, and fatty acids with 20 to 36 carbon atoms found in soils or sediments can point to life from higher plants, as seen in peat deposits, which come from plant waxes. Life itself creates a variety of biosignatures, such as nucleic acids, lipids, proteins, amino acids, and kerogen-like substances, along with different physical patterns, all of which can be identified in ancient rocks and sediments. Microbes in particular play a role in shaping the chemical environment around them, leaving behind features that serve as clues to their existence. For example, bacteria can create tiny pores in carbonate rocks that look like inclusions when viewed under a microscope. These pores are distinct in size, shape, and pattern, often swirling or branching, making them stand out from ordinary fluid inclusions found in rocks. A biosignature might be a pattern or feature that suggests life was involved, though it's also possible that it could have been created by non-living processes. One possible clue to discovering life, either in the past or present, could be the shape and structure of certain objects. The form and size of these objects may offer hints about whether life once existed in a particular place. For instance, microscopic crystals of magnetite found in the Martian meteorite ALH 84001 have sparked one of the longest-running debates in science about potential evidence of life on Mars. This meteorite contained what some scientists thought might be fossils of tiny rock-like structures. These structures resemble bacteria in shape, which made them an interesting candidate for being signs of ancient life. However, most scientists now believe these structures are simply too small to be fossils of actual cells. From these debates, a common agreement has emerged. Just the shape and structure of an object, or its morphology, can't be relied upon alone to prove the existence of life. The interpretation of these shapes is often subjective and can lead to mistakes. Scientists now agree that to make extraordinary claims like finding life, more evidence is needed alongside any morphological data. Morphology alone is no longer seen as a foolproof tool for detecting ancient life forms. No single chemical or compound can definitively prove that life once existed. Instead, scientists look for specific patterns in organic compounds that suggest life was involved in their creation. For example, when cells break down, they leave behind certain lipids, fatty molecules, that are distinctive. These lipids, which are the remnants of cell membranes, show a clear pattern. They tend to be concentrated, have a consistent size, and consist of an even number of carbon atoms. Similarly, life forms only use left-handed amino acids, a pattern that could serve as a clue to past life. Biosignatures, or signs of life, don't always have to be chemical. They could also appear as unique magnetic signals that suggest life once existed. Chemical biosignatures are complex organic compounds, molecules made of carbon, hydrogen, and other elements like oxygen, nitrogen, and sulfur. These compounds are often found in substances like crude oil or petroleum, where they show a simplified molecular structure, a result of the long process of breaking down organic matter from living organisms. Each biosignature has its own unique characteristics. For instance, the way organic molecules turn into crude oil is a slow process, which leaves behind a specific pattern that can be traced. Most of these biosignatures have high molecular mass, which makes them stand out. Some examples of such biosignatures found in petroleum include compounds like pristane, steranes, and triterpenes. These compounds are produced through chemical processes that use organic materials as their foundation. For example, triterpenes come from plants, especially those from land-based flowering plants. When analyzing petroleum, scientists often look for these biomarkers in small amounts within the oil or its source rock. They use specialized techniques like gas chromatography and mass spectrometry to identify and measure these compounds. These biomarkers are important because they help scientists understand where the oil came from, how old it is, and the conditions under which it formed. They also help to determine the maturity of the oil and its source material. Because of this, biomarkers are sometimes referred to as chemical fossils, providing a sort of chemical record of the oil's origin. Geologists and chemists use these biomarkers to trace the history of oil deposits. The unique patterns of biomarkers in different oils can help them identify where the oil came from and how it migrated over time. These biomarkers are also highly resistant to changes in the environment, which makes them valuable for detecting oil spills in waterways or contamination in lubricants. However, it's important to be cautious when analyzing untreated rock samples, as they may be contaminated or degraded over time, leading to inaccurate results. The study of exoplanet atmospheres is crucial because these atmospheres offer the best chances for us to detect signs of life, such as indicators of habitability and biological markers. Over millions or billions of years, life on a planet changes its chemical makeup in a way that's unique, something no ordinary chemical processes could achieve. For instance, Earth's atmosphere has large amounts of oxygen and smaller amounts of methane, both of which are produced by life. The color of an exoplanet or its reflectance spectrum can also serve as a sign of life. This is because life forms, particularly those that use sunlight for energy, like plants, have special pigments that give off unique light patterns. Scientists use Earth as a reference when looking at distant planets, often comparing how Earth appears from far away to how other planets might appear. Additionally, ultraviolet light can cause certain life forms to glow in a way that's visible in space, a phenomenon that new space observatories might soon be able to detect. Some researchers have discovered ways to detect gases like hydrogen and methane in the atmospheres of faraway planets. However, to truly understand these findings, we must consider the planet's environment and how it works. For example, finding both oxygen and methane together on a planet might be a sign of life, as this combination is difficult to form naturally and would indicate a major imbalance in the planet's chemistry caused by living organisms. Some of the top candidates for atmospheric markers of life include chemicals like dimethyl sulfide and chloromethane. Another possible biosignature could be the pairing of methane and carbon dioxide. Scientists are also investigating the presence of phosphine in Venus's atmosphere as a potential sign of life. When a planet's atmosphere has an unusual balance of gases, it could be a sign of life. On Earth, life has dramatically altered the atmosphere in ways that other natural processes can't mimic. This kind of imbalance or disequilibrium can point to a biosignature. For instance, the methane on Earth is much more abundant than it would be if it were only a product of natural processes. This is because living organisms constantly release methane. On another planet, if methane levels are much higher than expected, it might indicate life. Since Earth is the only known planet with life, we tend to look for signs of life based on the substances and gases life on Earth produces. However, life on other planets could be very different from ours and still leave detectable markers. These are called agnostic biosignatures because they don't rely on life being the same as we know it. Scientists believe that all life, no matter how strange, needs a source of energy, which requires some form of chemical imbalance. These imbalances are essential for life to survive. Geological processes, which are unrelated to life, help scientists understand what a planet's natural state of balance should be. If the planet's atmosphere strays from this balance, it may indicate life is at work, and this could be a universal sign of life, even if the biology is completely unknown. Detecting signs of life on a planet, like finding a biosignature, is a major discovery. But just as important is discovering that a planet does not have life. Life depends on redox imbalances, where some chemicals are more likely to gain or lose electrons to convert available resources into energy. If there is a redox imbalance but no life to take advantage of it, that's called an anti-biosignature, and it tells us something valuable about the planet. One interesting idea is the polyelectrolyte theory of genes, which suggests that DNA or similar genetic materials need to have a special structure to evolve through natural selection. In 2002, scientists Stephen A. Benner and Daniel Hutter proposed that for a genetic material like DNA to evolve on any planet in the universe, it must be a polyelectrolyte. This means it contains repeating charged parts that help it work in water. Benner and others even suggested methods for looking for this type of genetic material on planets like Mars, Enceladus, and Europa. One of the most debated topics in the search for life on Mars is the presence of methane in its atmosphere. Methane is tricky because it breaks down easily in a planet's atmosphere due to sunlight and other processes. If there's too much methane for it to break down, it might point to an active source. Since life on Earth is a major producer of methane, finding a similar imbalance in methane levels on Mars could be a sign of life, or at least something interesting happening. Since 2004, various spacecraft and ground-based instruments have detected methane in Mars' atmosphere. The levels found range from tiny amounts, between 0.24 and 0.65 parts per billion, to as much as 45 parts per billion in some places. However, recent measurements taken by advanced instruments on the ExoMars Trace Gas Orbiter did not detect any methane at all, setting a new limit on its abundance at just 0.05 parts per billion. This result contradicts earlier findings and adds to the ongoing debate about methane on Mars. Even more puzzling is the fact that current models of how chemicals break down in Mars's atmosphere can't explain the appearance and disappearance of methane in such a short time. To figure out if the methane on Mars comes from living things, scientists would need a lander or probe with a mass spectrometer to measure the types of carbon in the methane. By comparing the amount of carbon-12 and carbon-14, they could determine whether it's biological in origin, much like how scientists on Earth identify methane from living organisms. Mars' atmosphere also contains high levels of carbon monoxide and hydrogen, which are reducing molecules. This means there's energy available, but only life with the right kind of metabolism could take advantage of it. The fact that these molecules are there but no life seems to be using them supports the idea of an anti-biosignature. Scientists argue that this points to the possibility that life doesn't exist on Mars, or at least hasn't been detected yet. Astrobiology, or the study of life in space, is based on the idea that signs of life found beyond Earth will be recognizable as evidence of extraterrestrial life. A biosignature is a clue that could indicate life once existed or may still exist somewhere in the universe. For a biosignature to be valuable, it needs to be something that life would create, and ideally, it should be very unlikely that non-living processes, called abiotic processes, could produce the same result. To confirm that we've found proof of alien life, whether from the past or present, scientists must prove that a biosignature was created by living organisms, not just a natural process. Like most scientific discoveries, proving the existence of extraterrestrial life will take time and evidence, which will gradually eliminate all other possible explanations. In the 1970s, NASA's Viking missions to Mars made history by being the first to try experiments specifically looking for biosignatures on another planet. The two Viking landers carried 3 experiments each to test for signs of life, such as metabolism. Unfortunately, the results didn't provide clear answers, leaving scientists unsure. Currently, NASA's Curiosity rover, part of the Mars Science Laboratory mission, is working on understanding whether Mars could have supported life in the past and whether life might still be possible today. The rover is searching for biosignatures on the Martian surface, using a variety of instruments that can detect possible signs of life. These include traces of ancient organisms, like cells or fossilized remains, microbial mats, organic molecules, and gases that could have been produced by living things. Curiosity focuses on areas of Mars where organic matter might be preserved in layers of rock, increasing its chances of discovering fossilized signs of life. Meanwhile, the ExoMars Trace Gas Orbiter, launched in 2016, is working to map the sources of methane and other gases in Mars' atmosphere. By doing so, it helps scientists narrow down potential landing sites for the Rosalind Franklin rover, which is set to launch in 2022. The Rosalind Franklin mission will drill up to 2 meters below Mars's surface to search for biosignatures, protected from the harsh radiation that hits the planet's surface. The Mars 2020 rover, which launched in 2020, is focused on investigating areas of Mars that might have once supported life. It will study the planet's surface and geology to learn more about its history, its past habitability, and whether any signs of life could have been preserved in the rocks. The rover will also collect important samples that could be returned to Earth for further analysis in the future. Looking beyond Mars, NASA's Dragonfly mission, proposed for launch in 2025, will travel to Titan, Saturn's largest moon. Titan has a thick, organic-rich atmosphere, and scientists think it may have the right conditions for early forms of life or prebiotic chemistry to form. Dragonfly will search for biosignatures in Titan's atmosphere and surface and explore the possibility that life could have existed or could still exist on this distant moon. NASA's Europa Clipper mission is a flyby project aimed at exploring Europa, one of Jupiter's smallest moons, with a launch scheduled for October 2024 and a planned arrival at Europa in April 2030. The goal is to investigate whether this icy moon could potentially support life. Europa is considered one of the top places in the solar system to search for signs of life because scientists believe it has a vast ocean beneath its icy surface, possibly containing 2 to 3 times the amount of water found on Earth. There's a lot of evidence supporting this idea. In 1979, the Voyager 1 spacecraft took the first close-up images of Europa. Scientists suggested that tectonic-like features on its surface might be caused by the activity of a subsurface ocean. In 1997, NASA's Galileo spacecraft detected a slight change in Europa's magnetic field. This was interpreted as evidence of a conducting layer under the moon's surface, which could be a salty ocean. In 2012, the Hubble Space Telescope captured an image of Europa showing a plume of water vapor erupting from its surface. The Europa Clipper probe will carry advanced instruments to confirm whether this hidden ocean exists and study its composition. These instruments will also help map Europa's surface and look for signs of tectonic activity linked to the ocean beneath. While Saturn's moon Enceladus hasn't been directly targeted for biosignature searches, it shares many similarities with Europa. There's significant evidence that Enceladus also has a subsurface ocean. In 2005, the Cassini mission detected plumes of water vapor shooting out from the moon's surface. These plumes were later found to contain salt and organic compounds. Further measurements in 2014 supported the idea of a vast water reservoir beneath Enceladus's icy shell. Future missions might be designed to search for signs of life on Enceladus, as its potential for habitability is an exciting possibility. As for life beyond our solar system, the closest potentially habitable exoplanet is Proxima Centauri b, located 4.2 light-years away. Although this is relatively close in cosmic terms, it would still take more than 18,000 years to reach it with current spacecraft speeds. Because of this, exploring exoplanets for signs of life is currently limited to observing them through powerful telescopes. To date, no signs of life have been confirmed on any exoplanet, but research in this area is growing quickly, especially with the launch of the James Webb Space Telescope in December 2021. While the Webb telescope can't detect some of the key gases in the atmospheres of exoplanets, like oxygen, it can still help identify possible clues that might suggest life exists. Looking ahead, new ground-based telescopes like the 30-meter telescope and the extremely large telescope will make it possible to study the atmospheres of exoplanets in greater detail. These telescopes will have the ability to analyze light from distant planets, distinguishing between true signs of life and false positives, such as oxygen that might be produced by non-biological processes. This could bring us one step closer to discovering life beyond Earth. A rogue planet, sometimes called a free-floating planet, FFP, or an isolated planetary mass object, IPMO, is a massive object in space that has the characteristics of a planet but doesn't orbit any star or brown dwarf. These planets are rogue because they wander through space alone, not bound by the gravity of a star like most planets we know. Rogue planets can come from various places. Some are born in planetary systems where they form just like regular planets, but for some reason they get ejected and sent drifting out into space. Others, however, may never have belonged to any star system at all, forming independently in the vast emptiness of space. The Milky Way galaxy alone could be home to billions or even trillions of these mysterious rogue planets, and upcoming space missions like the Nancy Grace Roman Space Telescope are expected to help scientists pinpoint their numbers more accurately. Interestingly, some of these wandering planetary objects might have developed in a way similar to stars. For example, the International Astronomical Union has suggested that objects formed like stars but too small to ignite into full-fledged stars should be called sub-brown dwarfs. One intriguing object could be an example. It might have been kicked out of its original system to become a rogue planet, or it could have formed independently as a sub-brown dwarf. Scientists use a variety of terms when talking about these objects. In the early research, terms like isolated planetary mass objects, IPMO, and free-floating planets, FFP, were introduced. While these terms are still widely used in most scientific papers, rogue planet is especially common in studies related to microlensing, a method that detects objects by measuring their gravitational influence on background stars. In public announcements or news releases, the term rogue planet is often chosen, but terms like wandering planet, starless planet, or free-floating planet can also be found. For example, in 2021, press releases describing the discovery of more than 70 rogue planets used different names to explain these elusive objects. The first discovery of isolated planetary mass objects dates back to 2000. A team from the UK, led by Lucas and Roche, found IPMOs using the Euclid telescope in the Orion Nebula. That same year, a Spanish team led by Zapatero Osorio discovered similar objects in the Sigma Orionis cluster using the Keck telescope. The findings were confirmed through detailed spectroscopy in 2001. Both these discoveries were groundbreaking and are now considered major milestones in the study of rogue planets. Before that, in 1999, a Japanese team led by OASA found objects in the Chameleon 1 cloud, but it wasn't until 2004 that a US team confirmed their findings using spectroscopy. There are a couple of ways to find planets that are not attached to any stars, known as free-floating planets. Two main methods used by scientists are direct imaging and microlensing. Microlensing is a technique that has helped astronomers discover these rogue planets. In 2011, Takahiro Sumi, an astrophysicist at Osaka University in Japan, and his team, which included researchers from the microlensing observations in astrophysics and the optical gravitational lensing experiment collaborations, made an important breakthrough. They used telescopes in both New Zealand and Chile to observe 50 million stars in the Milky Way. These telescopes included the 1.8-meter MOA-2 telescope at Mount John Observatory in New Zealand and the 1.3-meter University of Warsaw telescope at Las Campanas Observatory in Chile. By observing these stars, the team detected 474 instances of microlensing, which happens when a planet's gravity bends the light of a star it passes in front of. Out of these 474 microlensing events, 10 were short enough to suggest they were planets, each about the size of Jupiter, but with no nearby star. From their findings, the team concluded that there might be almost 2 Jupiter-sized rogue planets for every star in the Milky Way galaxy. However, another study suggested there could be as many as 100,000 times more rogue planets than stars in our galaxy, though this included many much smaller objects than Jupiter. In 2017, Przymek Moroz from the Warsaw University Observatory led a larger study, 6 times more extensive than the 2011 research. This study indicated that for every star in the Milky Way, there might be at most 0.25 rogue planets the size of Jupiter or larger. Then, in September 2020, astronomers reported an exciting first. Using microlensing, they detected a planet with the mass of Earth that was completely free-floating in space, unattached to any star. This planet, called Ogle 2016, BLG 1928, marks a major milestone in the study of rogue planets. However, while microlensing can tell us a planet's size, it doesn't provide enough information to study the planet in detail. To learn more about rogue planets, scientists turn to another method: direct imaging. Direct imaging allows astronomers to directly capture pictures of planets and objects floating freely in space. One of the main challenges with these objects is figuring out their exact mass. For example, to calculate the mass of a brown dwarf or an isolated planetary mass object, IPMO, scientists need to know its brightness and age. However, estimating the age of these distant objects can be difficult. Most IPMOs discovered so far are found in young star-forming regions. These regions are well known to astronomers, who can easily estimate their age. Most of these planets are younger than 200 million years old and are large, usually over 5 times the mass of Jupiter. These objects typically belong to types of brown dwarfs called L and T dwarfs. Some rare examples are even colder and older, such as Y dwarfs, which can have masses between 8 and 20 times that of Jupiter. One of the closest rogue planet candidates of this type is WISE-0855 to 0714, located just 7.27 light-years away. These cold, distant objects offer scientists a chance to learn more about rogue planets, but to do so, they need more accurate measurements and better ways to determine their ages. The first IPMOs were discovered in the early 2000s using direct imaging, particularly in young star-forming regions. These objects are thought to have formed like stars, which is why they're sometimes called sub-brown dwarfs. However, some scientists believe that there could be IPMOs that formed more like planets, but were later ejected from their birthplaces. These ejected objects would behave differently, not having the same speed as those that formed within their star-forming regions. They would also lack a surrounding disk of dust and gas, and would likely have higher metal content. Interestingly, older IPMOs like WISE J0830 plus 2837 show a high velocity, traveling at about 100 kilometers per second, which suggests it could have been ejected from its original star-forming region. Another object, WISE 1534 to 1043, moves even faster, at around 200 kilometers per second, raising questions about whether it could be an exoplanet that was ejected. However, its color suggests it is actually an old brown dwarf, rather than a planet. Scientists studying these objects generally believe they represent the low-mass end of the star formation process, but their exact origin remains a mystery. As technology improves, the study of these rogue planets will continue to reveal more about their mysterious nature and how they fit into the larger picture of our galaxy's formation. Most rogue planets are incredibly cold because they don't have a star to give them warmth like the planets in our solar system do. However, even though these planets are freezing, they still give off a small amount of heat. This heat is not visible to the human eye, but it can be detected through a special kind of light called infrared radiation. Infrared radiation is like the heat you feel when you stand close to a warm object, even though you can't see it. To find these wandering planets, scientists use advanced telescopes like NASA's James Webb Space Telescope. These telescopes are specially designed to pick up that faint, invisible heat in the form of infrared radiation. The James Webb Space Telescope is one of the most powerful tools we have for studying the universe. Unlike regular telescopes that mainly see visible light, the light our eyes can see, the James Webb can observe infrared light, which allows it to look through thick clouds of gas and dust in space and spot objects that would otherwise be hidden. By scanning the vastness of the sky for any traces of infrared signals, scientists can detect rogue planets that are far from any star. These planets are often lost in the cold, dark reaches of space, so detecting their faint glow can be a challenge. But with the help of the James Webb Space Telescope, which is much more sensitive than older telescopes, scientists can now find these mysterious planets that drift aimlessly through the cosmos. Some planets in our solar system, like Jupiter, are known to produce strong radio waves. This happens because of their powerful magnetic fields. Magnetic fields are invisible forces that surround a planet, and they can influence particles in space, such as electrons. When these particles move through the magnetic field, they can create radio waves, which are a type of energy that travels through space in the form of electromagnetic waves. Jupiter's magnetic field is one of the strongest in our solar system, much stronger than Earth's. In fact, Jupiter's magnetic field is so strong that it traps high-energy particles from the Sun, and these particles spiral around the planet. As they move through the magnetic field, they generate radio waves, which we can detect using special instruments called radio telescopes. These radio waves are often so powerful that scientists can pick them up from Earth, even though Jupiter is millions of miles away. But it's not just planets like Jupiter that can produce these radio waves. Scientists believe that rogue planets, planets that don't orbit a star and instead drift through deep space, could also generate radio waves. Since rogue planets don't have a star to provide them with light or heat, they are much harder to detect with traditional methods like telescopes that look for visible light. However, if rogue planets have magnetic fields, they might still be able to produce radio waves, just like Jupiter does. Advanced radio telescopes, which are specially designed to detect these radio waves, could be used to find rogue planets floating in the vastness of space. These telescopes are incredibly sensitive, able to pick up even the faintest signals from distant objects. The signals from a rogue planet's magnetic field might be weak, but with the right technology, scientists could potentially detect them. In fact, radio waves from these planets could be the key to discovering objects that we can't see with regular telescopes. One of the most exciting things about this possibility is that it opens up a new way of finding planets. Right now, most of our discoveries of planets come from detecting the light they emit or the way they affect the light of nearby stars. But detecting radio waves could give us a whole new method to locate planets, including ones that aren't orbiting a star at all. This could lead to the discovery of many more planets in our galaxy, helping us learn more about how planets form, what they're made of, and how they survive in space without a star. Moreover, this technology could help us understand more about how magnetic fields work in space. We already know that magnetic fields play an important role in protecting planets from harmful solar radiation, as they shield planets from the sun's dangerous rays. By studying the magnetic fields of rogue planets, scientists could learn more about how these fields protect planets and what makes them strong or weak. This could provide important clues about the conditions needed for life to exist on other planets, whether they have a star or not. If planets can be kicked out of their solar systems, it's only natural that their moons could be affected too. Imagine a planet being ejected from its home in space and its moon being stuck to it, traveling together through the universe. While this might sound far-fetched, it's actually possible. Some moons might stick with their planets as they drift through the vastness of space, continuing their cosmic journey together, even though they're no longer in their original solar system. But what about the moons that don't stick around? Sometimes the gravitational forces of other massive objects in space, like nearby stars or even other planets, can pull on a moon. This force can be so strong that it breaks the bond between the moon and its planet, sending the moon off on its own path. When that happens, the moon becomes a rogue, meaning it's no longer bound to any planet. It drifts freely, moving through space by itself, with no planet to orbit. A rogue moon, unlike a rogue planet, is much harder to spot. That's because moons are typically much smaller and don't shine with their own light like stars or planets do. Since they don't emit any light, they're pretty much invisible to the naked eye or even to most telescopes, unless they happen to be near another bright object. As a result, they would be extremely difficult to detect, making the possibility of discovering them an even greater challenge for astronomers. However, if rogue moons do exist, they could be incredibly important to our understanding of how planetary systems form and break apart. The fact that a moon can be separated from its planet and go rogue suggests that the universe is much more chaotic than we might think. It shows that celestial bodies, no matter how small or large, are constantly influenced by the forces around them, and sometimes these forces can create unpredictable outcomes, like moons being lost from their planets. In many ways, rogue moons could be the cosmic forgotten travelers of the universe, silently drifting through space, carrying secrets about the volatile and unpredictable nature of our galaxy. Finding one, or even discovering a system of rogue moons, would open up a new chapter in our understanding of the cosmos. Although rogue planets don't orbit stars, they are still a fascinating and crucial subject of study for scientists. At first glance, it seems impossible for a planet that drifts alone in the vast, cold space without the warmth or light of a star to support life. But scientists believe that under the right conditions, life might be able to survive on a rogue planet. For instance, if a rogue planet has a thick, dense atmosphere, it could trap heat from its own internal energy, much like the warmth from a planet's core. This would allow the surface of the planet to remain warm enough for liquid water, which is essential for life, to exist. Some rogue planets may even have hidden vast oceans beneath their surfaces, similar to the ones found on moons like Europa and Enceladus, orbiting Jupiter and Saturn. These oceans could provide a warm, sheltered environment where life could thrive far from the light of a star. By studying rogue planets, scientists can learn a lot about how planets form and change over time. If many planets are cast out of their original solar systems, it suggests that the formation of planetary systems is far more chaotic and unstable than we once thought. This new understanding could shift the way we think about how planets and stars are born and destroyed. One of the greatest mysteries in the universe is dark matter, an invisible substance that makes up a large part of the universe's mass, but is undetectable by conventional means. Some scientists believe that rogue planets might help us solve this puzzle. Due to their massive gravitational pull, these wandering planets could bend the light from distant stars, a phenomenon known as gravitational lensing. In recent years, astronomers have made some truly thrilling discoveries about rogue planets that don't orbit stars and drift alone through space. In 2021, scientists made a remarkable find when they spotted a rogue planet, about the size of Jupiter, traveling freely through our Milky Way galaxy, far from any star. This planet was completely isolated, giving researchers a rare glimpse into the mysterious world of rogue planets. Then, in 2023, scientists uncovered evidence suggesting that rogue planets could actually outnumber stars in the universe. This finding challenges what we once thought about the way planets are formed and how they exist in the vastness of space. Looking ahead, exciting space missions like NASA's Nancy Grace Roman Space Telescope are on the way. These missions are expected to uncover even more rogue planets, potentially changing our understanding of the universe over the next few decades. With cutting-edge technology and new discoveries just around the corner, the mystery of these nomadic worlds continues to captivate scientists and skywatchers alike. Dark energy is one of the most mysterious and intriguing concepts in modern physics. It's something that scientists have been trying to understand for many years, yet we still know very little about it. Dark energy makes up a vast majority of the universe, yet we can't see it, touch it, or directly measure it. In fact, most of what we know about dark energy comes from its effects rather than its actual properties. To explain this in simple terms, imagine you are standing in the middle of a room and someone is pushing you from behind. You don't see the person, but you feel the pressure, the force, and the movement. In this analogy, dark energy is like the force that's pushing, but we don't know exactly what it is or how it works. Instead, we see how it affects the universe. Dark energy is an unknown force that makes up about 68% of the universe. If you think of the universe as a giant pie, dark energy is the largest slice. Despite its enormous presence, it is invisible and undetectable by traditional means. Scientists cannot observe it directly. So how do we know it exists? It all began with an unexpected discovery in the late 1990s. Two independent teams of scientists, working on separate projects, found something that changed the way we understood the universe. They were studying distant supernovae, which are powerful explosions from dying stars. These explosions can act as standard candles, meaning they can be used to measure distance in space because their brightness is consistent. When the scientists measured how far away these supernovae were, they made a shocking discovery. The supernovae were farther away than expected. This meant the universe was expanding faster than anyone had thought. The key to understanding why the universe was accelerating was the presence of dark energy. It's thought that dark energy is pushing the universe apart, accelerating the expansion of space itself. This was a huge breakthrough, as it challenged previous beliefs that gravity, the force that pulls everything together, was the only major force at work on a cosmic scale. At the heart of the mystery is the question, what is dark energy and how does it work? To answer this, we need to look at the nature of space itself. Space isn't just empty, It has its own structure and properties. Think of space as a fabric. Just like a stretchy cloth, this fabric can expand or shrink. When space expands, everything within it moves apart from everything else. This is what scientists mean by the expansion of the universe. But here's the twist. Dark energy is thought to be the force that's actually pushing space to expand faster and faster. Scientists have compared dark energy to the force of a balloon being inflated. As the balloon blows up, the rubber stretches and points on the balloon move farther apart. In the universe, the galaxies are like the points on that balloon. As space itself expands, the galaxies move farther from each other. This process has been ongoing since the Big Bang, when the universe began. But there's something unusual about dark energy. It doesn't behave like the other forces we know. Gravity pulls things together, while electromagnetic forces make positive and negative charges attract each other. Dark energy, however, has a repulsive effect. Instead of pulling galaxies toward one another, it pushes them apart. This repulsive force seems to be stronger as the universe ages, making the expansion of the universe accelerate over time. Even though dark energy is a major player in the universe, scientists still don't fully understand what it is. There are several theories that try to explain this strange force. Theory of cosmological constant. This theory was proposed by Albert Einstein, who first introduced the concept of a cosmological constant in his equations of general relativity. Einstein originally thought that the universe was static, not expanding or contracting, but later abandoned this idea when he realized the universe was actually expanding. However, the idea of the cosmological constant remained, and it was later revived to explain dark energy. In this theory, dark energy is a constant force that fills space uniformly without changing over time. It's like an invisible energy field spread evenly throughout the universe. Another theory, quintessence, suggests that dark energy might not be constant but instead could change over time. This idea is called quintessence. Quintessence proposes that dark energy is a dynamic field, something that evolves and changes, much like the way a magnetic field changes in strength and direction. In this theory, dark energy would be a kind of energy fluid that flows throughout the universe, and its effects could vary depending on the time and place in space. Some scientists believe that dark energy might be connected to extra dimensions beyond the 3 dimensions of space and one of time that we experience daily. According to this theory, there could be additional dimensions that we cannot see or experience. These dimensions might be influencing the expansion of the universe, and dark energy could be a consequence of the way those extra dimensions are interacting with the known universe and the modified gravity. Another possibility is that dark energy might be a result of modifications to our understanding of gravity. Some theories suggest that gravity doesn't behave exactly the way we think it does on very large scales. Perhaps the force of gravity is weaker than expected, causing the acceleration of the universe's expansion. In this view, dark energy might not be a separate force at all, but rather an artifact of our incomplete understanding of gravity on cosmic scales. Despite its elusive nature, scientists have found several ways to study dark energy. One of the most important tools is the observation of distant galaxies and supernovae. By studying the light from these objects, scientists can measure the rate at which the universe is expanding. As mentioned earlier, this discovery in the late 1990s was one of the key pieces of evidence for the existence of dark energy. Another important method is the study of the cosmic microwave background, CMB, which is the faint afterglow of the Big Bang. The CMB gives scientists insight into the early history of the universe. By examining the patterns in the CMB, scientists can make predictions about the overall structure of the universe and how dark energy might be influencing its expansion. One of the most exciting tools in the search for dark energy is the Dark Energy Survey, DES, a project designed to map the universe and measure the effects of dark energy. Using advanced telescopes, scientists are collecting data on billions of galaxies to better understand how dark energy is affecting the universe. Additionally, the Euclid mission, launched by the European Space Agency, ESA, aims to study dark energy in more detail. The spacecraft will gather precise data on the shapes, sizes, and positions of galaxies across the universe. By mapping the distribution of galaxies, scientists hope to uncover more clues about the nature of dark energy. One of the most fascinating aspects of dark energy is its potential impact on the future of the universe. Since dark energy is driving the acceleration of the universe's expansion, it could eventually lead to some dramatic changes in the far future. If dark energy continues to dominate the universe's expansion, it could eventually lead to a scenario known as the Big Rip. In this scenario, the expansion of the universe would accelerate so much that galaxies, stars, and even atoms would be torn apart. This is a long way off, but it's a possibility that scientists are considering as they study dark energy. On the other hand, if dark energy were to weaken over time, the expansion of the universe could slow down, eventually halting and then reversing. This could lead to a big crunch, where the universe collapses in on itself, with galaxies, stars, and planets being pulled back together. But the truth is, we don't yet know what will happen. Dark energy is still a mystery, and we are just beginning to scratch the surface of understanding it. Finally, dark energy is one of the greatest puzzles in modern science. It makes up the majority of the universe, yet we can't see it or measure it directly. It is the force driving the accelerated expansion of the universe, but its true nature remains unknown. Whether it is a constant energy field, a dynamic force, or a consequence of extra dimensions, dark energy is a key piece of the cosmic puzzle. As technology advances and our understanding of the universe deepens, we may one day unlock the secrets of dark energy and understand how it shapes the universe and its future.